this will prove to be the most informative and helpful meeting of the ones that we've had to date. Let's take care of a little bit of housekeeping stuff. For those of you that have not attended, we do record this meeting for YouTube. It's available live stream, but it's also be available online for, I don't know, indefinitely as far as I know. So if you do happen to ask a question, make sure that you speak clearly into the microphone. If you're a presenter, always be aware that
All right, thanks, Tom. So what I want to do right now is sort of go over the water quality of Torch Lake. That's where we'll start off, describe all the stuff we've been collecting over the last 3 years. When I go through this, there's going to be lots of information. So it's going to almost feel like you're in a college class, a limnology class. I'm going to go over the physics, the chemistry, and then the biology, and go all the way through that, hopefully in a way that's understandable, and one that'll just sort of see how it just grows up on each one of those. What I'm talking about today is information that I collected very little of this. Jim Wilkinson has led most of it. He's out there collecting anything from what we see out here.
Sorry.
So he's collecting all kinds of information, everything from what's in the lake to what's in the rivers. And then we also got a lot of support from the people as part of the TLPA. There's a lot of things that we wanted that were local, and it'd be very hard for us to collect it. So we had a number of people, and I'll try to acknowledge them as I go along. So I want to talk about the current water quality. And when I do that, it's mostly relying on these 3 years of data. But wherever I can, I'm going to try to go backwards and try to describe how things have changed through time. Okay. One of the main issues or concerns that almost all lakes have is this whole problem with eutrophication. And eutrophication is this process going from a lake like Torch Lake to a more and more productive system. And what we see is that this process normally takes over the millennia. It takes a long time for this to happen. But it doesn't take a lot of input from the watershed, from people around the lake, to make this whole process go really quick. And what we really are doing here is trying to either slow that process down or even reverse that. And that's a big part. So I'll be talking a lot about nutrients and how this process works. And this is also an issue here at Torch Lake. If we look at it, it's, if you go online, it's a jewel of the north. But there's a lot of growth coming around. There's a lot of cottages around it, and there's a few people that are loving it to death, okay? And what we're trying to do is to try to find out what all these factors either are doing to it or could do to Torch Lake. This is just a picture of a sign that I took from the side of the lake, and you can see some of the major concerns deal with that eutrophication. They're worried about algal mats starting to grow, worried about green algae on the shoreline and rocks. So maybe it's not a real prolific kind of thing, but that is a concern. Now, because of that concern, there was a study that was done this was published in 2006, and it's very similar to what I'll be talking about today. In that study, they tried to document the water quality in 2005, 2006, which is sort of a great reference point. Now, there's been a lot of sampling that goes through time, tip of the mitt, others, but most of that is a fairly short-term studies, whereas this one was a short in time, like a month here, a month there. But in this 2005, 2006 study, it was very elaborate, trying to really document the water quality of the lake, and they realized that phosphorus loading could be an issue, so they tried to document that. They also wanted to see how the lake should respond to those changes. Now, a lot of the stuff that we'll be doing is very similar to that. But now what came out of that study is they knew they had some weaknesses. They tried to do as best they can, but they were saying, we did the standard data collection. That should be continued on, really. Field and laboratory quality control, they realized they had some problems with the lab, and other people would also. This is an extremely clean lake. And most labs cannot handle getting down to the concentrations that are out there. The concentrations I'll show you today on most of these dealing with phosphorus, most labs would just say less than detect and walk away from it. They also said choose parameters for long-term trend monitoring and continue monitoring the ice cover. So as a sort of following up on all that, there was still these issues. Even after that study was done, there was these issues. And so a group of people got together, most of the people that are, almost everybody's in the room, and basically got the USGS involved to go back out there and relook at that, try to come up with a long-term monitoring plan for the lake, but also document the water quality and see if it's changed and why it may have changed. So that sort of led to our study today that I'll be talking about, which is basically our data collection is done, our analysis and our publication is just in the process right now. But the first goal of that was to document the water quality, talking about that right now, of not in the open water of the lake, but also the nearshore areas, and quantify how much vertical mixing, how much one system. I'll tell you why we're looking at phosphorus in a few minutes. And then, not just stop at the Clam River, but look at all sources. GLEC tried to look at this, but there's things that weren't included, let's say like septic systems, and we're trying to put numbers to that. Then, this is something, again, that GLEC did. They came up with a lake response. If we change the loading to lake, how will the lake respond? If we come out here and all of a sudden we have twice as much phosphorus coming in, what can we expect the lake to turn into? And then finally, we'll talk a little bit about the effects of the biota. The effects of the mussels. Mussels are continuing, population is increasing. How can the loading affect the mussels, and how can the mussels affect what we see in the lake? And then finally, just a little bit, we'll look at GBA and try to talk a little bit more about that. And how, what that might be the causes. Tom's got, Tom and I and a few others have came up with a hypothesis. You've heard Jan speak in the past. He's got an idea, and I think some of the stuff that we have sort of fit together with that. More what kicked off what Jan was talking about. Okay, so now if you go back to that GLEC study, if you looked at what I was just, all my goals, they really do match the GLEC study. So what we're doing in a big way is redoing the GLEC study, and because of that, there's so many similarities. I'm going to go back and forth a lot, especially not so much this morning, but more in the afternoon, and try to say, okay, why is this study similar to GLEC study, or what's different, and what are the implications on how the lake works? Okay, so in terms of our monitoring, it was very simple. We're going to go out and sample the lake. In addition to sampling the lake, we're going to sample the near shore. We're going to look at the loading from all the streams coming in it. Use that to estimate how much is coming in from other areas, how much is coming in from groundwater, how much is coming in from atmospheric deposition, how much is coming in from septic, how much is coming in. We have a lot. So I'm going to try to talk about all these things. What we try to do is to look at all of these kind of things and quantitate it, and go through and come up with really numbers to describe all of these sources and really describe how this lake works. Okay, so to start off, I'm going to talk about the water quality of basically the middle of the lake. When most people look at water quality of lakes, this is what they're referring to. And we have really two sampling sites. We got our main site right here, which is over the deep hole. We have a north site that we're sampling, and I'll show you in a little bit, but we put out a thermistor string on the lake to try to see the short-term fluctuations in temperature, and also a little bit of the sloshing of the water around. So when we go out, this is one of the few times that I was on the lake, and I get out there and I'm over here in a snowmobile suit and everything else. But then I find out this is how Jim samples. He gets out there and he's like sampling in the Caribbean. You can see. So anyhow, but yeah, I'll leave it at that. So, okay, let's go back to this. The first thing I'm going to talk about is the physical limnology. How the temperature stratifies, how the mixing and light changes in the lake. Come on. Okay, so if you go into the lake, let's say a couple weeks ago, most deep lakes, what they do is they start off and they're totally mixing. As the wind blows down, Yes, Torch Lake is 290 feet deep or something. And the wind blows, it'll mix that water top to bottom. The water will completely mix during spring overturn. Then, as things warm up, it begins to stratify, and it'll break down into 3 layers. You got this warm layer, the uplimnion, a mix, the thermocline, where there's a rapid change, and then the bottom. Come on. And now the reason why a lake stratifies goes back to the physics. And this is how the density of water changes with temperature. As you can see, once you get above 4 degrees, basically 40 degrees Fahrenheit, it becomes lighter and lighter. So that means that warm water wants to float on top. Okay? And so that's why we get this epilimnion developing. It's as the water gets warmer, there's a bigger density difference, and so that water wants to float on it, and it keeps to mixing until that wind is not strong enough to mix it any further. At that point, it stratifies until the water cools down, and then as it cools down, we get into this fall mixing, and then finally we get into in some years, the ice cover forms, and we'll get stratification underneath that. Okay. So this is very typical of any deep lake. You got spring mixing, and as it warms up, you get to stratify. Well, how does Torch Lake work? Well, this is Torch Lake. Now, if you look at it, this is what we see in the springtime, mixed top to bottom, no difference at all. And then it stratifies as the summer goes on, and we get a very strong thermocline. And you can see at this point, it's about 23 degrees at the surface with a huge temperature range. Come on. Okay, start to combine with the carbonic acid to form that calcium carbonate. All right. So now we finally get to the one I really wanted to talk about. If you look at what's driving this whole process, going from a oligotrophic lake down, it's really driven by nutrients. So that's one of the things we really wanted to monitor very closely. Whoops. Now, when we look at this is for Trish. When we look at this, there's really several different types of nutrients out there. You could look at things like carbon, nitrogen, phosphorus. And so this goes back quite a while ago, in the 1970s, there was this big debate about what's driving this. What is the major factor causing this? And so that up in Canada, they could do a lot of things that we can't do around here. They split this lake in half, and these kind of things. But anyhow, this is what happened. If you look at where we collected data, that's these blue dots. But there's a lot of other people that have collected data. I mentioned the GLEC study. That's these other light blue dots over in here. But then there's a lot of other ones. Tip of the Mitt is out there, Michigan DNR. So there's a lot of change, a lot of people collecting data. And when you try to put it at and just look at the summer averages, they're bouncing around. This is because there's probably only one sample collected. But it's really hard to pick up any change. Is there a change as we go through there from the beginning in the mid-1990s? Maybe. But the data out here are definitely not going to tell you this. Now, if we would have had all the data going to the lab and the lab is doing what they're doing today, we would have been able to probably pick it up. But right now, trying to well, this is the total, the dissolved. Like I said, it's getting harder to measure this. You're down to 1 microgram per liter. Basically, getting really close to the detection limit. But it looks like there is a little bit, maybe a dissolved phosphorus in it, but it's still quite low. So that was phosphorus. Now when we look at nitrogen, nitrogen is a different animal. You look at this, the total nitrogen. Before we were talking about 0.003. Now we're looking at 0.4. Okay, so that's a factor of about 100, at least 100 in there, difference. And if we look at how much is dissolved, that's basically this nitrate value, we're up around 0.2. And the important thing here is that it doesn't really drop below 0.2. There's always lots of nitrate in this lake. All right. How does nitrogen fit in the long-term picture? Well, this gets a little bit harder. Most people don't measure that. So we do have tip of the mitt, and they measure it consistently during the springtime. And we measure it through here. And it stayed pretty consistent, but we have seen some pretty big bounces. I don't know exactly what's causing a few of these big things, but we have seen a few changes. Overall, I don't see any real trends, but there is some bouncing around in it. Now, one of the questions that comes up with this, if you go back to that earlier study, what's really driving the productivity in the lake? And there's a couple ways to look at it. One is to go through and sort of look at how phytoplankton take up nutrients. And that's, they mix all these things together and they make sort of the algal material. So you're taking carbon, nitrogen, phosphorus, water, putting it all together to make basically a phytoplankton kind of thing. Now, when you look at that and you're trying to figure out what is the potential limiting nutrient, you say, well, okay, if you look at what an algae is made up of, it's made up of 1 part phosphorus, 16 parts nitrogen, and 106 parts carbon. So if you look at that, that means that if you took all the nitrogen, these nutrients in the lake and started using it up, they would use it up at that rate. They should use it up at 1 to 16 to 106. And so if you have a lot of nitrogen around, it doesn't matter because it's that one part of phosphorus. Now, in all the numbers I showed you, that's when you mix it all together. But now if you compensate that phosphorus is heavier than nitrogen and so forth, well, then you have to correct for that. And so if you look at a mass, that 16 to 1 ratio turns into about 7 to 1. Okay. So that's if we're looking at milligrams per liter of each of those. Another way to look at this whole thing is simply forget about all that and just look at the amount of dissolved phosphorus, dissolved nitrogen in there, and say which one runs out. If one runs out, that's obviously the one that's controlling things. So if we look at that ratio, well, we come up with the magic number. Remember, if I said it was about 7 to 1. Studies say there's different kinds of algae, different this, and so they raise that up to about 9 to 1, depending on what kind you have. But we're up to about 300. So it's not even in the ballpark. So it's definitely saying that phosphorus, if you ran it and took everything that's in there and just ran it until it was all taken up by biology, you'd run out of oxygen or run out of phosphorus first. So in this case, phosphorus should be the potential limiting nutrient. Oops. If you looked at it in terms of the dissolved, now you're looking at nitrate versus a phosphorus. Phosphorus is so low that it's really tough to say whether that's really present or just a little bit cycling around. But it definitely looks like if you're looking at a limiting nutrient, phosphorus is again. What kind of phytoplankton, what kind of algae are out there? So now to do that, we're trying to find out if there's green algae or blue-green algae. And what we did is we took our samples from all those 4 locations, sent them into Phycotech for analysis. And then we sampled from April through October in the first year, went into December the next year. But we wanted to see what kind of species out there and how much is it. We knew it was low. You know, everything, the chlorophyll is extremely low. So we know that the amount of algae is going to be low. But what we see as we go through the year, we had very little algae up until June. Okay, that's why we have such great water clarity out here. Once we get into June, all of a sudden we're picking up at least some algae. And what we're seeing is a combination of golden algae and blue-greens. Now, some people would say, oh, that's blue-greens. That got to be terrible. Well, every time we do a lot of times what people call green algae is really blue-green algae anyhow. And so this is what we're seeing out in the middle. If we look at that in terms of percent breakdown, again, early on in the year, these numbers were a lot lower. If you look at during April and May, they were low, but there was a lot of diatoms in the water column and golden algae. As we get into the summer, the amount of diatoms drop off and the amount of blue-greens take off. So it is low, but now at least we can tell you what kind of species are out there. Now, how about near shore? This was a real concern. Is there a lot more algae by near shore versus offshore? Well, we can measure with chlorophyll. We just wanted to look at in terms of the types of algae that are out there. And for the most part, it's not really much different. And we don't see that the near shore has a lot higher concentrations. If you look out in the north, this is the North Bay. I had already presented the south. Maybe the wind was blowing a little bit and caused the blue-greens to be higher on the north side than the south. But for the most part, we're seeing very similar in the 4 different locations. Okay. I guess the important thing is that we're just not seeing the higher concentrations in the near shore. Okay, if we look at that, we wanted to compare the 2 years. If you look at the breakdown in the species, very similar between 23 and 24. And if we go into up here, it looks like it's almost the same, but you have to look at these axes. And this is just for, well, when you look at this, this goes up to 2 million, this goes up to 20 million. So it was a lot more productive in 24 than it was in 23. But these numbers are still really low compared to other lakes. Okay. How about the zooplankton in there? That's these little dinky bugs. If you looked under with a magnifying glass or even more, you could look and see exactly what those are. And so when we did that, we went out there and sampled. We didn't get a lot of them. These are actually very low numbers. And when you put those in terms of biovolume, it's basically all we're seeing out there is copepods. But if you look really close and change the axes and said, okay, is there anything else out there? So copepods are going from 0 to 600,000. This is going from 0 to 0.0 almost. So it's just really low. But there are a few other kinds of things out there. We're seeing a few cladocerans and a few rotifers. But for the most part, Torch Lake is really dominated by one thing, which is the copepods. So if we look at the 4 places in the lake, there's a little bit of variability. Whenever your numbers are that low, you're going to see that variability. And the one thing that comes out is that near shore seems to have a few more rotifers. So if you're into this stuff, that's a little bit of a difference. Okay. Difference between years, not much at all, except that in 1 month we picked up quite a few cladocerans. And that means that that's the kind of algae, if you're really looking at things, you'd really want those because those are the sort of the vacuum cleaners going through. And in 24, we picked up these kind of things that could go out there and actually eat the algae. Okay. All right. So the take-home message is that the chlorophyll in the lake has been very low throughout the entire time period. Chlorophyll is the same basically throughout the entire epilimnion. Phytoplankton is dominated by blue-green algae and golden algae a little bit earlier on. Yes, diatoms are there in the springtime, but they're not near what you're seeing a little bit later. It's just that they're, like right now, we have a water clarity of 20 meters out there. That's saying there's just not much diatoms out there. If we had a lot of diatoms, the clarity wouldn't be as good as it is right now. And the zooplankton are dominated by copepods. If we were to have a lot more algae, that's when it's something else you might be out there, something to eat them, but we just don't have much out there for them to eat anyhow. Okay, the next thing I wanted to look at is that almost everything I've described has been in the middle of the lake. Do we see much difference in all these other places around it? So what we did is that when we were collecting all the data out in the middle, we're also going around taking almost the same kind of samples at all these other places around the lake. First thing we want to look at is all the basic stuff. Temperature, specific conductance, DO, pH. And if you look at it, bottom line is there wasn't much difference. The only thing we really saw was that at this NO7 right here, just north of the Clam River coming in, we see a little bit higher specific conductance. That's really the only thing we saw in all that. We see a little bit higher concentrations up right in here, which is weird because that was the lowest phosphorus concentrations, but a little bit higher chlorophyll. But if you look at those differences, again, those are extremely small differences. So overall, there's very little difference between the nearshore and the offshore part of the lake. Take home there is near water quality is basically similar. It's something to be concerned about because if things get worse, you'd expect the nearshore to get worse faster than the offshore, depending on how much mixing there's going on. And 7, which is near the Clam River, had slightly higher specific conductance. And that's probably because when you're coming in, there's a combination. I'll talk to you a little bit about groundwater. Groundwater has someplace have higher specific conductance, and that could lead to some local stuff near shore. And NO3, which is that site up by the highway north, had slightly higher phosphorus and chlorophyll concentrations. But again, it's just a very small difference. Okay. Now we've looked at all the stuff, the water quality of the lake. Let's move out into the tributaries. We want to look at what's coming in the Clam River, Spencer, and what's leaving at the outlet. Whenever I start this kind of thing, I like to look at the weather conditions. And for the weather, we decided not to pick one little weather station. I decided to pull it out of a national database. This is called NLDAS. And they try to take everything they have available to it, integrate it to a specific latitude and longitude. And from that, we can get an idea of how much, this is the precipitation in the area, All you do is you pick a latitude and longitude, and you get that on an hourly basis through time. And if we look at that, it looks like it has increased through time a little bit. And overall, where do we see the precipitation during our study? Lower than the average for that time period, but higher than, there's a gradual increase in precipitation through time. But overall, we got pretty representative years. 24 is a little bit lower, 25 is a little bit higher. If we look at the Gleck study for a little bit later, it would have been about 2004, 2005, but they picked a little bit different. We're using water years, which goes from October through September. They used a little bit different water years, so I calculated it the way they did it, and it would have been a little bit drier period. Okay. And then finally, how warm was it during those years? You can see here's that global warming that's occurring on. If you look at the overall air temperatures, and overall, they're pretty warm years. Okay. The important thing in our study, though, is that those temperatures are much different. But if you look at the temperatures in the wintertime, they're quite a bit different. We had a fairly warm 24 followed by a warm 25. And that followed up. We had no ice cover in this year, and we had ice cover in that year. And so that does affect some kind of things. And for the ones that people are interested in this year, that's over there someplace. So we didn't include that, what's happening right now in it. Okay. So let's look at the inputs then. Here's our Clam River gauge. If anybody's been over right where the Clam River comes in, you can see our solar panels out here. Down here we have, down this track, we have something called an acoustic velocity meter. Sends out beams, and from that we can figure out how much water is moving through it. Some people want to go out here and just say, well, what's the water level? Because there's always a relationship between water level and discharge. Not here, because it's controlled by the lake right downstream. So you can't just look at the water level and figure out how much. Water level is important because how much is going through, but you can't get that relationship between flow and discharge. So that's why we had to go through and add this little bit more sophisticated meter. And as I'll show you, it was probably the most important thing that we did in terms of this whole study was put this gauge in. Okay, so from that we can get not only discharge on a daily basis or a monthly, we can get it I think we're measuring it probably every 5 minutes. So with that, you can see it bouncing around a little bit. And that's due to because that sloshing I was talking about. So that might sort of back water up back and forth. And so we see period. One of the things that Fred will ask me right away, well, what happened last month? Well, sorry, the gauge is gone. But when we're up here, we're at about 800 CFS. My bet is that we're up here about 1,600. So it was just too bad. Well, in some ways it would have caused, we'd be still sampling today in terms of trying to see the effects of it. But that's what you need in order to really get a really good handle on how things are changing. Now, on top of that are the red dots. This is how every one of those is a water sample that we collected. So we got a lot of water samples. This is how many times we collected it. So during our study, we had an average discharge, if anybody's interested, is 357 CFS for those 2 water years. Now, what we want to do then, though, is take that and combine it with our phosphorus samples. We told you we collected, and nitrogen and other things, but we have these samples. Here are the concentrations associated with each one of those. So what we end up doing then was filling up, we just connected the dots. Since it's downstream of the lake, you really don't have to worry about big fluctuations between the dots. But we connected all those dots, then multiplied the flow times the concentration every 5 minutes, and then add that all together, and we can figure out how much phosphorus is actually coming down through the river. And when we did that, that's the way we get our loads on a daily, monthly, and annual basis. And we're all done. We end up with phosphorus loading from the Clam River being 2,400 kilograms per year. At the outlet, we basically had the same thing. You can't measure it just by water level. We have our acoustic Doppler meter out here, and we're able to measure the flow. Same thing, we got it on a 5-minute basis over that. This one we had a couple small breaks, but you don't see it in this time series when somebody decided to drop. I think they dragged it. No, they smashed it with a boat, right? Yeah. But anyhow, we sort of did that. Luckily, we got it right back online. I think it was only offline for 2 days during the entire study. And here's the outlet, the discharge coming out the outlet. And you can see all the samples we collected. And again, we multiplied one by the other to get the total load leaving it. So first of all, we have an average flow of 457. So we have more water leaving the lake than coming in. That's because it's got everything in the Clam River, plus stuff from rainfall, plus groundwater and other things, and all of that. So we end up have more leaving than coming in. What's that? Yeah, 100 some CFS more. And the total phosphorus load is about 2341. We put that all together. Now these numbers I'm talking about, I don't want you to write them down. That'll be after lunch when I put them all together. P loading in the river going downstream. So whoever's downstream of this, they would look at it as P loading in the river. Yeah. Okay. Yeah. Right. So they get that. Okay, so what we end up with, if you look at that, we have 357 coming in, 457 leaving it. So 100 CFS difference coming out. If you look at the loading, we have 2,400 coming in, 2,300 leaving. Now, this is just the river. It doesn't include what's coming in Spencer and all these other places. So there's not more leaving the lake than coming in. Okay. All right. What's that? The lowest is about 200. About 200 leaving. Oh, if you're looking at some of these kind of things, but well, that's a little bit of bouncing up and down, like this kind of stuff, up and down. Oh, there's different times, but yeah, I wouldn't say on an average overall, it's 100 CFS more. I would never look at any of these things down to a small part. Okay. So now let's go to Spencer Creek. So that's the big one coming in and going out. We wanted to look at Spencer Creek, which was sort of our representative of all the streams coming in. We're going to sample, I'll show you in a little bit the other ones, but we couldn't measure the flow. So at Spencer, here's Spencer. And if you're looking at the bridge from there, you can see this little bit of thing over here. That's just our staff gauge. Behind the scenes, this is our sampling thing, our sampling gauge. It's an ISCO sampler. If you followed there's a hose that goes under there and it sucks water all the way out from the river. So we can collect that water. Basically, we have a program set up to tell it when to sample, but when the flow goes up, it collects more samples. And then, whoops. Thought I had, no, I guess I don't. So we end up with a lot more samples at this site. If you look at it, so we sample that, and whenever the flow went up, it looks like we have one sample, but very often we had a number of samples on that day. So when we looked at it, we've seen a big change. So we're collecting something at low flow, middle, and high, and then we integrate all of that. And the reason we do that is very often, if you looked at this is not from Spencer because it would be all clear. You wouldn't see it. But here's a dirty one, but typically in a storm, the concentrations go up and come back down. They do that in Spencer. You just wouldn't see it. But that's why we collect multiple samples during the day. And so what you really want to do is to get those enough mean concentration of 14. I'll tell you what that, or 0.014. I'll tell you what that means a little bit later. And the annual load is about 66 kilograms per year. So quite low. It's a small stream, but that's probably what's coming in and depending on its area, coming in like Wilkinson and Eastport. So now what I'm ultimately doing is here are all the factors that can drive that water quality. I've talked about what's coming in the river, what's out there. But now we got all these other factors out here. We got other things that we weren't quantifying. How about that nearshore runoff? Well, if we look at the nearshore runoff, that's this whole idea in this purple. So we subtracted off Spencer. So we took Spencer out of the thing. We still got all this other area. And it's about 4 times the area of Spencer. So what we did then is 5 minutes, okay. So then what we did is we sampled these 2 streams here, or actually 3, because we got these 2 in Agami, and we wanted to figure out what the water quality was like at those. And those special thanks to, we had a crew that went out there. Yes, we had our people going out there on a sort of a quarterly basis, but we had Bob and Trish and Peg going out there sampling these streams so we can get a time series of those. So we don't have as many, but we weren't really trying to get a load the traditional way. We just wanted to see what the concentrations were. So when we did that, we put it all together. We measured phosphorus, dissolved phosphorus, Kaldol nitrate, and total N. For the most part, these are when we get over to this side, this is all the USGS sampling. The phosphorus is a combination of the two. Okay. So the thing that's really important here is that in all these streams, the concentration is really low, 0.006. We never saw a concentration of higher than 0.031, which is extremely low. So if you're looking at a river coming in, these are very low concentrations. Now I wanted to get the load from this unmonitored area. So for that, I basically took a drainage area and said, well, Spencer's, all this other area is about 3.5 times what Spencer is. So we took Spencer times 3.5 to get the flow, multiplied it by a concentration of 0.06, and we get a total load from this entire nearshore area of 107, not including Spencer. Okay. Now we wanted to get, still didn't feel really, this is where it gets a little bit of fuzziness, that all these houses are around the lake and they must be contributing something. And we don't really have that. So what we ended up doing was going out there and we wanted to figure out the area of houses. We just assumed that we had basically 311 hectares, which was about 1,500 houses times about a half acre. And then we went into literature and said, oh, everybody's done these studies all over the place to get an export rate. And from that, the one I thought was the most representative was 0.2, based on some studies we did in Wisconsin and other place. You put that together, the houses around the lake are putting another 60 kilograms. So we try to represent all of that. Hold on. All right, so take-home message, nutrient concentration, all the tributaries is really low. The Clam River dominates. So if you're gonna monitor one thing, that's what you wanna look at. Now let's move on to another one, atmospheric deposition. Okay. Now, in most studies, they blow this off, saying there can't be much in atmospheric deposition. But if you look at the GLEX study, they showed that was quite important, so we definitely wanted to look at it. And to do this, we end up installing a site right over here at the Torch Lake Airport. Here's our fancy equipment. Tom started sampling this at first, and we switched over to another Tom. So we had the twin Toms looking at this. And through that, by doing all of this, we're able to come up with a really good time series of the concentrations of phosphorus in there. And you can see the blue is the phosphorus concentration in the rainfall. The green is, there's some calculations behind there, trying to get how much is coming in dry fall. But the important thing is that the maximum concentration we ever saw was 0.011, so very low concentrations. The average rainfall concentration was only 0.003. The average snowfall concentration was almost nothing. And I think that's because most of the snow is coming off of direct evaporation off of the Great Lakes with no phosphorus in it. And so we end up with very low. And so we can put that all together and come up with how much is coming in from precipitation. I don't see a number there. Oh, well. I'll talk about how much that equates to a little bit later. Or maybe I'll do it here. So yeah, here it is. So in rainfall, we end up with the wet part, 153 kilograms, a little bit coming down in dry fall, and overall 166 kilograms coming down. Okay, how do the years fit into the long-term picture? In terms of atmospheric deposition, I was trying to look at why is our number so low? Well, if you look at a site, this is actually up in Canada. If you look at, there is a trend in concentrations in a sort of a pristine area, and it's dropped a little bit. Well, it's actually quite a bit. It dropped about 40% from 2005 to 25. And the reason why I picked those years, that those are the GLEC years. I was trying.
Don't talk about septics over at Higgins Lake. All right. Good deal. Good deal. All right. So I presented this figure back in 2024. I used a different model that I'm going to be presenting later on today to inform where we're going to look at groundwater in Torch Lake. So this is a dissertation that a colleague out of Michigan State University presented or created back in 2019. He's now at the Corps of Engineers down in Mississippi. It was a regional model that, as you can see, it was a very large region. So Torch Lake is a very, very small part of this. Because of that, we're not really able to use it for the kind of purpose that y'all are interested in. So, but we can use it to look at where we want to put our sites. So this model that I'm showing here was relatively coarse, really big cell sizes. So Torch Lake would have several cells, but not a really local look. And yeah, like I said, I presented this in early May of last year, or 2 years ago. So we use this to update where we would put groundwater locations, sample locations for Torch specifically. The idea was to capture areas that would be very informative for groundwater input, both for volume and for nutrients. All of our sites were located with collaboration from y'all, both with where everyone was interested in and permissions. So we need to access everyone's land, tromp out there, run water in and out until it runs clear and it can kind of settle down. The relaxation phase is actually that. The whole bottom needs to relax, chill out, become regular, normal, lake bottom again before you can start sampling it. So this process took it has generally a lower DO, but Dale will talk a little bit about that later, and a higher specific conductivity. So the lake water has about 350, and the groundwater can have 500 to up to like 1200. So it's not easy, but it's you can see that you're getting groundwater and not surface water. We have our sampling system right here. So you can see we have a flow through system. So we pump out the water and keep it from contacting any air, going through this flow through cell so we can get undisturbed measurements. A little bit of a cartoon of what that looks like. So like I said, it's about 2 feet down. Our piezometer is about 1 foot in height. It's under the lake, so it's in the water versus on the land. That's to get where the groundwater system is contacting and going into the lake. Like I said, these sites are semi-permanent, so we go out, we install them, and we leave them. We don't take them out and come back later. This allows the groundwater system to be sampled multiple times, and it reduces error. So if you come to a spot and you think you're in the same spot, and you put it down a piezometer, you may or may not actually be in the same spot. So with these, you leave them out there and you're sure you're sampling the same spot over and over. We went out several different times through 2024 and 2025, even in early January of 2026. I tried to get Jim to go out there many other times in the winter, and yeah, what wasn't happening. We sampled several different things, in situ measurements of temperature, pH, DO, and conductivity. This is our setup, so we have to, again, drag out some pretty heavy stuff. Our peristaltic pump, we don't have a field pump, which is easy to carry. We have a lab pump, so we had to bring out a car battery to run it. Again, sampling from a dock is way easier than sampling from the land, where we have to we have a little boat that we float out and carry all our stuff. Again, we have our sonde that we use our peristaltic pump. There's the well that's, we have these bricks that we put over the top so nothing can come and yank it out easily. The tube comes out, we have set up a table so it's easier to sample. Again, we have to drag all of our stuff out in a little boat and run the water through the flow through cell. At that time, we can also make sure that we're getting groundwater, because if you pump the water too hard, you slurp the lake water down into there and you're not sampling what you thought you were sampling. We did some grab samples that also Dale will be talking about later. Dissolved phosphorus, nitrate, nitrite, ammonia, and chloride. We measured how high the groundwater level, it's typically called groundwater head. It's really hard to measure it in Torch Lake. It's also hard to measure it in Higgins because it's really clear. Dale has a message. The water here, this first picture, you can kind of see if you squint and look really hard. And we're in a room squinting really hard. The sun's not your eyes. There's not boats all driving around. It's really hard to measure this stuff. We did a little bit of MacGyver work and floated Jim did all this MacGyver work, floated a cork so you could see it when you're out in the distracting field. Long days, heat, sun, annoying boats coming and waving you. Yeah, so site disturbance and waves also makes the lake water also really hard to measure, because if the lake's going up and down, what number is that? High, low? So you try and kind of average it, but again, it's pretty hard to measure. The results that you're looking for are, is it above the lake water? Is it below the lake water? Is it right at the lake water? And that can tell you a lot about if the groundwater is coming in quickly, if the groundwater is leaving quickly, if it's kind of like a little of both. So some of the results from this is across the map, these are all of our sites. The bright pink is where there's higher outflow. The blue or bright blue is where there's higher inflow. And all those gray ones are where it's, about the same. These numbers are also pretty small. So interpreting this is still very, very small, like Dale was saying. Like there's just a really little difference in some of this stuff. So in that northwest area shows that groundwater is actually losing. It's the lake water is going out in your area, like going towards Lake Michigan. The central area, these blue are stronger input areas, gaining from the surrounding area, but most sites are within about a ½ inch of the lake surface. Again, there's a lot of caveats with this in that it's really hard to measure. Okay, so the model. This is the model that I created for this specific project. The objective is to describe the pattern of the groundwater input spatially around the shoreline and to estimate a total input to the lake. So we have several inputs that I'll go over in visual format here in a sec. There's surface water features like rivers and lakes you put in. There's recharge, which is the amount of rainfall that comes down and turns into the groundwater. Hydraulic conductivity, think of that as the difference between cheesecloth and canvas. So if you've got canvas, water doesn't go through that very easily. If you've got cheesecloth, water can move through that a lot easier. And then all these little dots are observed groundwater elevations from water wells. So people come out and you get a new water well, and the driller will report information to the state. That's a publicly available resource that we can then also use in our model. So building the model, the first thing, there were several iterations of building this model. It's hard for me to say that we're done modeling because you're never done modeling. You can always tweak a little bit more, but at some point deadlines happen and I have to come up here and show you guys what I have. So the first thing is building that model boundary. Where is not important? How far out do you have to go before it really doesn't affect Torch Lake that much? So there's this pink area that we call the near field. That's where we think for sure everything's gonna matter to Torch Lake. There's this gray hashed out area, and these lines are all drawn by surface water boundaries at this point. So this area is important, but not as important. So you don't have to be so specific about that, like getting information and stuff. The surface water features, obviously lakes and rivers. Then the first time we made this model, kind of came pretty close to out here. Turns out this area is pretty important as well. So we had to expand it. This ugly brown line is the actual final model boundary. And we'll see a little bit later why that's important. Recharge, this is based on that 2019 model. There's a lot of variation across this model area between 20 inches and negligible. So like there's not a lot of recharge that happens in a lake because it's the lake water. It's not coming from rainfall. But for the model purposes, we just came up with a single zone for recharge. So this whole area was just modeled by 14 inches a year, which is about average for that area. hydraulic conductivity, that's that cheesecloth versus canvas sort of analogy. What is the truth? What is down there? We're not exactly sure because it's below the surface of the earth. So again, we use some geologic formations from a historical report, the Frand and Bell report, if anybody's into geology. These lines are each a geologic formation that you could assign a conductivity measure with. But the model, when I made all that, put all that complexity in, didn't like that. So the model didn't do very well, didn't perform very well. The final model, this whole green area was modeled as a single zone, and this like peachy area had a different conductivity value. So what is the truth? Does the model tell you the truth? Do these maps tell you the truth? What is truth? These are those groundwater elevations from the water wells. It's called the WellLogic database. It's super awesome. Has a lot of data in there. It's got lithology in there as well, but it's a little bit harder to work with. So these are observed levels of groundwater. So I plotted it up, and you can see that there's this area where the groundwater elevations are pretty high, and it kind of peters down into some pretty low levels down by the lake, kind of what you'd expect. I pulled in Grand Traverse, Calcasta, Antrim, and Charlevoix counties because y'all span a pretty big area. A lot of political area. So how does the model look? Again, you can compare the modeled elevations on the y-axis versus the observed observations on the x-axis, and they've lined up pretty well. So there's a black line in here that's covered by the red line because the model is pretty good. So that black line is the one-to-one. You'd want everything that's 200 meters measured in the observed to actually be modeled as 200 meters. There was a little bit of an error, especially down in the bottom, the lower levels. It's just a very slight under prediction. These could be things that we tweak more, but again, deadlines. So this is where the cool stuff happens. These are some of the results from the model. These are groundwater contours. Kind of think of it as a topography. So if there's a hill, you have a lot of lines. This area, again, is a pretty high groundwater table, and you think of it as like a slide going down. So our sites are located in those pink marks. Torch Lake is kind of at the bottom, if you think of it like that. As a large contributing area up here in these higher areas. Higher groundwater elevations along the western side of Torch. It's kind of like another hill, kind of blocks the movement. So I'll show you here in a sec more. And the northwest area is lower, where these contours kind of open up to the Lake Michigan. So you can also put in particles and see where those particles go. These are following, this is modeled information. I also put up some, you can barely tell, these dots, this dot here, it's gray in my picture, but it didn't turn out. These are hand-drawn divides that are hand-drawn, but they line up really well with the where the flow paths are headed. A lot of the same sort of things. So looking regionally, these particles that I plopped up here can go down into Torch. Sometimes they curl around and go up into Clam. Some short flow paths, they follow that hill that I was talking about. A little bit of complexity here where they're a little bit short. There's some curling up in here, some straight. So lots of information that you can take a groundwater model and look at and use. That's why I put objective at the very first slide of this groundwater, is that we have specific objectives that I was focusing on. Looking closer, so this is the same stuff, only zoomed in. Some of the cool stuff, we didn't put any particles up here. I should have put some particles there to make sure they go, but they're going out to the lake from the top of this divide. There's curling up here that comes in into one of our sites up there. There's, like I said, there's a lot of cool stuff that you can look at. And I'm sure y'all are looking at where you live, where you have information. Peg talking about your artesian wells. So you have a lot of arrows that are coming in over there. So that's probably supportive of the artesian wells. I think my next one's even prettier. So this is also pretty cool. This is these are line segments that are divided. That's kind of choppy, but each line segment is summarizing how much inflow is for that specific line segment. So you can make your lines bigger, smaller, depending on what you're interested in. The rainbow colors showing low inflow, so low inflow of groundwater into that line segment versus high inflow, groundwater coming into that segment. Also outflow and where it's kind of here or there. So like I said before, these areas up in the northwest, there's generally the water is leaving the lake and headed out to Lake Michigan. Areas in the southeast where there's a higher inflow from that that large area off to the east. Generally, if you look at it, these greens, you have a lot more inflow from on the eastern side than on the western side. These colors are all a little bit more on the low side. Let's see. So the model agreement with areas reported to have springs and artesian wells. And for a total inflow, we came up with the model came up with 84.3 CFS outflow, and this is groundwater, about 0.4 CFS, so not that much. And for a whole net inflow of groundwater into the system, about 83.9 CFS. I think that's my last one.
Is that an average for the year?
It's a single point in time. That's one of the things you can do with groundwater models. You can change them in time, but this is just one snapshot.
Because I know we took samples at different months, and I didn't know how that average, how that number was influenced by the various hydrostatic tests.
Exactly. Yeah. So that's one of the things that you can tweak and change up a little.
Thank you very much.
Sure.
And I'll also try to follow up on a question you just asked, Tom. Okay, so what I want to do is really quickly before we go to end this is try to take everything that Sherry did and now add the water quality to it. She mentioned we did a lot of sampling out here for a lot of different kinds of things. So we're measuring the head, which was trying to just to confirm that the model was on the right track. But even more so, it's going to be how we use the data, because some of these sites, although the model says one thing, if we got a head going the other direction, we might not want to use that water quality to look at what's coming into the lake because the water's going the wrong direction. Okay, so go a little further. Here's that a picture of what Sherry was saying. If we go down her sites, this is that head, how much it's going into the lake or out of it. And what we're seeing is that this is the area around the east number 3. That's the one over on the middle of the east side that has a big head over there. And over on the west side, there's an area that has a lot more flow always coming to the lake at that time. Other ones are pretty small. So there is a lot of variability out there, but we want to use this more to get an idea of which of these concentrations do we measure or do we use to estimate what's getting into the lake. For example, we don't want to go over by W1 and say, here's what we wanted. We'll use that concentration because what's going into the lake, it's going the wrong direction. So we don't want to use those numbers. Okay. So in general, E3, W2, and W3 are good sites to say what's coming into the lake. Okay. And here are those areas. So we definitely don't want to use that site. That's interesting for a model, but we don't want to sample it. We sampled it for an understanding. We don't want to use that to estimate what's coming into the lake. These are the ones that we want to rely on. Okay. How about dissolved oxygen? That was one of the first things we measured out there. If we look at that, there's a lot of variability out there, but there's some sites that when we first got this, we said, oh my gosh, didn't expect this at all. We got a lot of sites that are anoxic. E1, there's no oxygen in there any time of the year. All 6 samplings, basically are anoxic. That's important when we looked at how much septic systems are coming in. There's no oxygen. There's not much to slow that phosphorus down. So we look at that, and there's a lot of sites like that. They might have one that bounces up, but in general, all these sites are really close to anoxia. And here's all those red sites, and you can see a lot of the sites coming in are anoxic. So any of the water coming through that system, or if you have a septic system by it, it's not going to stop much phosphorus. It's going to keep on going. So this was sort of a real eye-opener. We wanted to look at which sites. We didn't try to hit septic systems. We actually tried to stay away from them. Well, I shouldn't say it. We didn't try to hit them. So we were looking at this as more of a background kind of thing. But we wanted to see which of these sites that we sampled might be hit a septic plume coming in. And one way to look at that is to look at the specific conductance. You can sort of see an average coming through here. This is a really high one. So this, it turns out it's E5. That's probably got in the middle of a septic plume. We didn't really try to do that, but we think we hit a septic plume with this one. E1, we might have hit another one. You can see that sometimes it's right on the edge of it. Sometimes it looks like we're in a septic plume, sometimes we're not. Okay. And chloride goes along with that. So E5 is definitely saying that that is a site that we probably hit a plume, just be aware of it. And E1, maybe. Okay. So if we look at that, these are the two sites that look like they really have septic influence coming in. Okay. Next thing we want to look at is a dissolved phosphorus. That's really why we did this whole thing. At least why I did this whole thing. I was pushing because we wanted to take these numbers and figure out how much phosphorus is coming in with those. So we got a lot of range on those. I know it's noisy. But when we look at that, these three sites seem to have the highest concentration if you average all those together. You know, through all 6 samplings, these 3 sites are a little bit higher than the other ones. Okay. But when you average all that together, you get a concentration of 0.006 milligrams per liter, 6 micrograms per liter. And again, those are very low concentrations. I'm not saying where any site is by. Okay. All right. So what we did is we did a lot of sampling out here. We measured all kinds of things. And here's these, all these have a little bit of meaning. The reds are all low dissolved oxygen. Here's a site that I said has septic influences. You go through this. And now we want to say, I'm going to use all this information. And then we had other people that came in here like Wayne. He said, well, why don't we try to relate this to GBA? Can we collect a little bit more sampling? So in 1 August, we went out here and measured things like iron, manganese, magnesium, molybdenum, and other things. So we went out there in August and sampled a number of other things, hoping we might find a correlation with some of that. And I'll talk about that a little bit this afternoon. So what I wanted to do then was to take what Sherry just presented in terms of flow. So we got all these things coming in, and we get a pattern, and try to take that and say how much phosphorus is coming in with it. Now we know that a lot of those heads were, sort of really close. So what, at least as a first shot at this, what I did is I said, let's take these 3 big ones and only use the data from those sites. So we took those times the average concentration here. Right now it's just the average, but I actually did do a seasonal estimate, trying to figure out how much phosphorus is coming in with the groundwater. Okay, so we collected that. It's interesting, but we didn't use the water quality at these sites. Okay. Now, as it turns out, if we had taken the overall average or those 3 sites, it was the same number. They're both 6 micrograms per liter, 0.006, so it doesn't really matter. But to do this then, we want to estimate the total phosphorus input from groundwater, total flow times the mean concentration. Here's what I was saying, if I take the 3 big heads coming in, we get 6. If we took all 12, we'd still end up with 6. So it's pretty low. So from doing this whole kind of thing, if we do not assume there's seasonal variability, we come up with 327 kilograms per year. And that current concentration is that. So the take-home message is that natural groundwater inputs of phosphorus appear to be a much smaller source than previously estimated, and that's because of that 0.006. We had a very low concentration before. I think they averaged like 0.04, so a lot higher. And much of the groundwater is coming in is anoxic, which is a concern, which means that a lot of people, that they have their septic plumes out there, or their septic plumes. That's my interpretation of it, because I don't have a house. They have a septic field out there. and that's coming in, when you have anoxic water, it doesn't stop the phosphorus very well. It'll just keep on going, and it's very little to stop phosphorus from getting into the system. And groundwater may have other implications. So I'm going to come back later on this afternoon, especially when we start to look at possible causes of things like GBA and try to put this together with that to say how it might affect the biology. So with that, I think we'll leave that in terms of water quality. And I don't know if we have much time for questions.
Perfect. Now it's time for questions before lunch.
And if we have a little chance, we might talk about other things that we can do with groundwater, but okay. Yeah, Rick? Here, Tom can be my.
So Dale, you showed clear evidence that there's, what appears to be an increasing pH trend in Torch Lake from 1990s to present, and kind of a, increase into the up, 8.5 now or something like that. Are we seeing that, or did you check to see if we see any of those kind of trends in other northern Michigan lakes?
Well, that's where
Um,
the tip of the mitt seem
Yep.
all over the place. And actually, Jan has, in one of his reports, talks about seeing it. That's why we also looked at Leelanau.
Yep.
That was, I'm looking for, when we looked at this, we tried to find somebody that was not using the same instruments.
Right.
And we see it there too.
Okay.
I
So,
looked on the east side, on the west side of the lake, I didn't see it.
okay. But so that evidence is true for most northern Michigan lakes or Michigan
But
lakes?
This area.
It's not unique to Torch is what I'm
This-
trying
yeah,
to say.
It's not unique to Torch.
Okay. All right. Then the second,
One of the things that we did do is we took the lakes that Jan has in his 20 lake study, and like Charlevoix, Mullet Lake, all of them on his list, and we have those historical records. But what Dale is saying is, if they're taken from the same people, the same instruments, we're not sure that we want to have confidence in that. That's why we went to Lake Leelanau.
Good.
But generally speaking, there's a lot of data, historical data, that does show pH trend. And we're still in the process of validating that, but everything still strongly indicates that that is a definite trend.
which would contribute to the calcium carbonate precipitation,
Yes.
so on and so forth. Yep. Yep. Okay. I've got lots of questions. I'm only ask one more. I'll hit
Okay.
Dale one-on-one. You showed the zooplankton data. The data you showed, does that indicate a healthy population? You didn't really mention what healthy or non-healthy is. What's
I don't
your
think- I-
view
you
for
see them in
Torch
all
Lake?
different kinds of lakes. I think if you looked at the LG, it might be a little bit different. But in terms of the zooplankton, I wouldn't say there's a healthy type of zooplankton versus another one. It's a lot driven by the fish, because the fish will eat, they're good at finding some kind of species and wiping them out. So in general, if you got a filter feeder, you're not going to see a lot of cladocerans.
But it's not a concern
No,
number.
no.
We got a question in the back.
Yes, thank you. Just as one brief comment to fill in with that pH, I'm from Higgins Lake, and I was very interested in this increase in pH. So I looked at all the available data for Higgins. We have an early indication from 1939, and then a bunch of spotty data since then. Looking roughly at the Higgins Lake data, I did not identify any that the same kind of change that is occurring. So it's just, nothing formal about that, but just an observation to be careful of not characterizing this as a northern
Right.
lakes.
The other
issue.
thing is,
So-
if you look at the Leelanau Lakes, depending on which years, you might miss it, because it was Leelanau Lakes. If you didn't look at the detail, you might not see it, because it seemed to be high. It dipped down and then it came back. So that's why it's not a real, yeah.
You want to talk to Sherry about the groundwater pH though, I'll tell you that much, because it wasn't in the report. Oh, that way, I'm sorry. There you go.
Hi, just a quick question on the nutrient budget. I saw that the estimated contribution of phosphorus from septics was 625 kilograms a year. but then the groundwater input was 327 kilograms per year. Were those two differentiated? Was septic contribution somehow filtered from those groundwater samples?
The theory is that the way we were estimating groundwater, we were missing all the plumes. We realized we probably hit a few of them. In general, we don't want to use that one that I was talking about that was from that area, which we weren't. So we don't want to stay away from those two sites. So as long as we stay away from those two sites, we think we missed the plumes. So that's background concentration. And then we added septic on top of that. So we were figuring that we missed all the septic plumes as long as we stay away from those two sites. Tom, there's one right there otherwise.
Oh. Along that same theme here of septic and plumes, despite all the incredible data that's been gathered for the last 3 years, I think one of the points of data we may not fully understand around the lake is the aging septic system. How valuable would it be if we were to sample a significant number, whatever statistically significant number of the septic systems, aged septic systems, let's just say, to really understand what that input of phosphorus may be contributing to the lake?
Here's my take is that all septic systems are old. There is no aging on a septic system unless you have a pump back. If you pumped it in and pumped it out, then it's okay. Other than that, septic systems are not designed to stop nutrients. Okay, if you think about it, you put them in, they leach through the water, right? If you're anoxic, there's nothing to stop it. It's just going to go through. I don't care if you just put it in today, it's going to go straight through. So in terms of an old septic system and new septic system, they're not designed to stop nutrients. There's a reason why you go out there. I can walk around with somebody and say, look how green the grass is here. Oh yeah, there's a septic field. It's right downstream. So when you look at this, septic systems, they're designed to keep the E. coli and stuff out of the water. They're not out there to stop phosphorus.
Right, but
So
isn't
in
it, isn't
terms
it
of-
presumed that more is leaching into the lake because of aged
No. Well, age, yes.
slash unmaintained or
Not-
ill-maintained?
Forget the maintain part.
Okay.
Age, yes, because what happens is if you've got this big bucket out here with a hole in the bottom, which is a septic system, right? It's got a plume that's longer. So if you had a huge bucket here and it's been leaching for 50 years, it's just what you're seeing is 4 years ago, 5 years ago. But it doesn't really matter if it's a new septic system or an old septic system, unless you got somebody out there taking all this stuff and taking out some of the nutrients. Even then, it's only taking out some of the nutrients. So the theory is that people think that if you put a septic system out, and unless it's flowing over the top, it's bad. Think about it. If you turn on your shower and keep it going, where's that water going? And if you have nothing to stop it, after they get old enough, all those little spots on particles have no place to grab phosphorus anymore. Once you're done with that, I don't care if you put in a brand new plume in that same area, there's nothing to stop the phosphorus from going through. So septic systems are given a different impression than I believe in. I don't care if it's a new one or old one. If you have a septic field that's been around for a while, it doesn't matter how old your septic system is.
So then the only real cure would be to put a complete system around the lake, like Tahoe did several years
Yep.
ago, that
There's a reason why we did
eliminates
it.
septic systems and individual yards.
Or pump it out. Yeah, that's the problem with it. When you're trying to keep concentrations this low, it's a problem. But no, that is a common belief that septic systems, once you got a failing one, for phosphorus, they all fail.
Thank you. Just on that, have you actually measured what you're saying?
Have I personally? No.
So that's what I'm. That's what
The
I'm
only way you
getting
can
at
do
is
it
that
is-
based on, say, the septic analysis done on Houghton Lake in '73, where they actually instrumented around septic systems, and they could actually see the attenuation or dilution, because it is two, and that was an extremely shallow water, very close to the lake. My question had to do with is that when you look at it, for example, in slightly deeper water, and I'll just use an example. I said, I've dug up my system, which I have as dry well, the sand beneath it is bone dry, but the entire tank was completely surrounded by roots. And one of the questions that comes into it is that if I want to really understand what's happening for any particular source of phosphorus, is I need to be able to put wells around it, like this study was done in '73, and actually look at it. Because I understand the generic thing of phosphorus absorption sites being saturated. However, that treats the soil as if it's dead. Anyway, so that's the only reason that I bring it up is that it seems to me that it's very valuable when you're making big decisions like this, is to actually instrument a number of systems to see what they're actually doing versus what we think they're doing.
Right, this was a potential study. If you looked at it, we're trying to get a potential from septic. We had 12 wells. If you really want to look at this, we needed 12 wells on each one of the septic systems. If you look at it, when they do those studies, I have seen it, you put up a whole row of them, not only there, but you have to do it with depth. And so all of a sudden, my 12 just turned into 60. So you need 60 wells for each septic system. We didn't have the money here. So this was trying to say, is our septic system something we should worry about? So I don't disagree with you at all. It's just that it's hard to measure. Yep.
Any more questions? All right.
Just one real quick one. This groundwater work, like you were saying, is just the sort of the start. We just try to get say, is this a good thing or is it not a good thing? Is this something that we should be worried about, especially with septic systems? We used a model that Sherry talked about, which is called G-Flow. Assumes that it's sort of a one-layer system. We didn't do anything with depth. That's something that if we really wanted to look at this, we wanted to bring that depth characteristic in it. We wanted to look at some of the more refined sampling. That was one of the first things that we thought is that if we really want to look at septic systems, like we had that one that had 1,500 specific conductance. The specific conductance there was 1,500. We probably hit the plume. If we would have gone 15 feet that way or 15 feet this way, we might have been back down to 500. So, but that's why sort of refined. Right now, we're looking at sort of the typical years, which is good. This year would have been interesting because a wet year, it would have changed a lot of these things, not only for groundwater, like right now, I'll show you a little bit later. I think on a typical year, there's no groundwater coming, very little groundwater coming in July. Right now, I think there's still a lot of groundwater coming in this year. But in a typical year, I don't think we'd see it. So I think there's other things that we could do as we go forward. I think as we look at a long-term plan for the lake, some of the things you bring up might be important.
Okay, one last call. Any more questions? Guess what? We're right on schedule. It's 12 o'clock. It's time for lunch. The people that we have moved over here at the round tables, if we could find you another place to sit, they want to use these tables for the food service. We have everybody's attention. Thank you.
Thanks, Tom. So I'm going to be super fast to keep us on time. And so I provided a text copy of basically what I'm going to go over. I will leave them on the table there for you to peruse at your leisure. I have been working on what we call a status of the fishery report for Torch Lake since we completed our last survey in 2018. It turned out to be a much more substantial undertaking than I anticipated. One thing that I very quickly discovered is we have a very lengthy management history on Torch that dates back to about 1881. And not a single stitch of it has ever been written up in a very comprehensive or publicly available format. So that includes about 18 different lake surveys that involved electrofishing or netting. It involves a couple of egg takes for lake trout and Atlantic salmon out of here. It involves a bunch of a fair amount of tributary stocking, fish stocking that goes back to 1881, and a whole host of other things. We did shanty counts, airplane counts, all these things. And so my goal through this project has been to put this all in one location. The status of the fishery reports are the only reports that are available to you guys to just log on to the DNR website and find. We do so many surveys and so much work annually, we simply don't have a website large enough to host every one of these individual surveys. But every one of these surveys that I mentioned in this little synopsis, all the data is tabulated. So there's a table for every one of these surveys and a brief little synopsis of it. Same thing for all the historical stocking. I put a couple images on here that are just snippets, excerpts from the document. You will notice the table on the back says Bennett Creek. And you're like, Heather, that's not a Torch Lake trib. I know it's not. But in our stocking records, it's listed as Bennett. However, the stocking coordinates for all the sites that they put fish in line up with Megason Creek. So I believe it's Megason. I'm waiting for our librarian in Lansing to verify that based off of the paper copy. I have a digital data sheet entry basically that gives me that stocking information. She has the hard copies from 1905. So I'm waiting for her to get me verification on that the name on the stocking sheet is wrong and the coordinates are right, or vice versa. So that is not just me not knowing my stream locations up here. But so along with that, my contact information is on the back of here if you have any questions. The draft of this document has been done since January. Was actually completed. I completed it last August. It went through a round of editing. While it was being edited, the Lansing staff found me more surveys. I went back and added those. It was completed again in January. It went to editing, and then April happened. So we were all redirected from our normal duties for quite some time this spring. So I talked to the editor this morning. We should have this publicly available by the beginning of July. So as soon as it is available, I will send it to you guys so that we can get it on the website and get a link to you guys so you can put it on the website and everybody can finally take a look at all. I think right now it's 58 pages. So.
Thank you very much.
Yeah.
Wait, whoa, should have been late.
Are you on that side?
Yeah.
Okay.
I'm probably on both sides.
No, I just messed up your screen. Make it smaller.
I learned I could do that.
Touch screen,
I
hate
did.
those.
I did not know I had it until last night. Honestly.
Here's your, I'm gonna shut.
Since I get this to appear.
It takes a few minutes to come up.
Come on, baby. I don't know, Tom. How long is too long?
You're not connected, right?
I don't know.
Put it in, try it, keep it over this one.
That one's not a port. Is it?
This is no signal.
Oh, baby.
It's just not connecting. Let me see.
See if yours works. Oh, yours works.
Okay.
Let's try mine.
So it's not the cable, it's just your connection. Well, we did.
Did I see you guys have HDMI to VGA adapter?
I do have one.
Well, the problem was we didn't have a female to male HDMI adapter. It was in his bag.
I think your HDMI is a male end to go into that.
Yeah, I have one.
Yeah,
that
but
goes
it
in
won't
that.
reach.
I've got a long cord.
If it plugs into the VGA cord, it will, right?
It's in your bag. No, your adapter, your white one that goes on here.
I don't have the way to hook to that.
That should go right into your computer.
Oh,
Other side.
let's try the other side.
Your computer just does not want to share it.
I know, that's why I'm going down to shut down.
It worked this morning.
Yeah, that's weird. I'm gonna shut it down and start over.
His file was too big to send me.
You said you got this morning between 10 and 11?
No, no, we decided that yesterday. Because normally I have everything on one computer.
Wow.
You mind if I drive real quick?
Sure, go for it. I got nothing right now. I was gonna shut down my machine and start over.
You should be able, if you were to,
It was working before, that's why I was gonna shut down and start over.
if you, with the
Think you
Windows
gotta
machine,
reboot it?
with the Windows machine, if you connect to this, you can cast straight to it. If you connect to, what did we say it was, this one, Tom?
Yeah, that's it.
I already put in a password before, that's why.
Okay.
I think we're better off just trying to shut off and start over.
You think you got to reboot your computer?
Go ahead. That's Windows for you.
That's why I have to. When I was a consultant, Business park tonight. We're getting ready to go to GM for a big presentation. For a system that we built on engine. And I went over, stopped at his house about an hour early, opened up the computer, we were doing some last minute updates. And he came up and said, we have to do a Microsoft update. Stop your whole life and we're gonna do an update. And we had to leave. And you couldn't stop it. Because if you did, it was gonna get screwed up and then you didn't know what to do. That's why I shut that off and scheduled all for middle of the night. Well, I just decided that day I was gonna go buy a Mac. I was learning curve. Very, very fast, no problem. Matter of fact, I would never go back. I won't. Well,
Did Dale break it?
yeah, Dale, no, actually, something happened with his computer. The safeguards in his computer, the government put in there, suddenly decided it didn't want to recognize that USB device. So they're the backup.
Mine is government free.
Yeah. Yeah, you don't need all that help from the government. No, I mean, he was up there for an hour and a half this morning and worked fine. He just connected it, tried to reconnect it, and wouldn't recognize the device. Some kind of a safety protocol. He never got that message before. But it says you're connecting.
If you do get connected, your presentation slides are going to flip slow too.
Okay. Well, at least you can try to work it on a wireless while you're not up here, right?
If he tries to connect wireless, I'll somebody else is doing it. Yeah.
We don't have a longer cord. I'm sorry, everyone, for the delay, but we had government intervention. Dale's computer is protected from some type of a nuclear attack or something, and it decided to no longer recognize the USB device that we're using, and it's now blocked the wireless connectivity. So all the backup plans have been prevented by our wonderful government. So we're gonna once again adapt. No, it's okay. We have one tube. Thanks, Leslie. So what we're going to do is we're just going to let Jan come up and give his presentation while we try to work on the technical difficulties. Oh. Well, so much for the government, huh? I don't like getting down there so much. I brought it up here. We just outsmarted the government once again. I wish I could do that on my income taxes. Can we go to full screen?
Jan, do you have a button? Oh, I can take that out.
That's for your keyboard
That's the mouse.
or mouse? Okay.
Okay, I'm all set.
Can you go to full screen? Here it is. Now you got it. All right, we're once again we apologize for the interruption. We're back on schedule now.
All right. Now what I want to do after this morning is sort of pull this all together. And I talked about the individual pieces of the water budget, the nutrient budget. Now what I want to do is to go through and put this all together and try to look at this and ultimately lead that to try to say, how should the lake respond to changes in nutrients? No? Okay. Okay. So this morning I talked about a lot of factors that are affecting water quality. I've got a whole series of things coming in. And what I tried to do this morning was provide that framework to say, what are those sources and how big are they? in doing this, whenever you're dealing a phosphorus budget, what you really want to have is a water budget first, and then put concentrations to it. Okay. So let's look at that water budget, and what it says is that we have a change in storage, and that we can get from our gauges. Our gauges, as part of it, we measure the water level, and so we can measure the inlet and outlet, and figure out what the total of change in storage is. And that's going to equal the water coming in from precipitation times the area of the lake. What's coming in from surface water, clams, Spencer, and unmonitored, and I talked about how we're trying to get all of those. Groundwater, now we have a groundwater model, but I actually have a water budget groundwater model, trying to get it down to the short-term timing on it. And then we have evaporation, which I haven't talked about yet. And finally, we have how much is coming out. So if we can measure all of those and then put phosphorus values to each one of them, then we can come up with a phosphorus budget. Okay. But we don't have evaporation. And so what I want to do is get evaporation first and then compute groundwater by difference on this whole thing. And we can do that to get the groundwater input on a daily basis. So how do we get evaporation? Well, if you go back to some of the earlier studies, they relied on evaporation pans, and there's some issues with that, because that usually works okay for a small lake. But if you looked on a big lake like Torch, it'll freeze, and your evaporation pan would freeze before the lake would. So instead of that, what I'm going to do is use a model called the General Lake Model, GLM. And in that model, what we do is we take all these inputs, which we're measuring. We have morphometry, meteorology, inflow, lake stage, outflow. And from that, I can compute things like water temperature, ice cover, and evaporation. Okay. So the first thing I want to do when I do something like that is show you that convince you that I can do the heat budget. And so this is the observed temperature, which you saw in a little bit different colors before. And now with the model, I can do a pretty good job on that temperature. And now as part of doing this temperature, it's computing evaporation in the background. Okay. So when I do that, here's my evaporation from Trout Lake. That's one of the lakes I worked on, but from Torch Lake. And you see the evaporation is fairly high in January, drops down to very little right now, and then it goes up higher later on in the summer. And that's pretty typical. The one thing that's weird is this January, February thing. Normally in most models that'll drop down to zero or very close to it because it's all ice. But when I ran this, I ran it for 2 years. 1 year it froze and 1 year it didn't. And this is the average of the two. So 1 year I'm gonna have a lot of evaporation and the other year I'll have very little evaporation. Okay. So now I have everything in there. Actually I have two of some things. So I have everything in here. Groundwater I now have twice. Okay. Because groundwater I have it from Sherry's model, but that's just a long-term average. So now if I use my evaporation, turn around and compute groundwater and do a little bit of smoothing because my change in storage has satious and things in it. Now I can get the groundwater input. So when I do that, here's the picture of groundwater. It's very seasonal coming in. Now remember, that's not this year. This year I would expect to see this number being a lot higher in the middle of the summer. But normally we have very low groundwater coming on during the summertime, and that's due to a lot of evapotranspiration going on out here. So in the summertime, what you have is all the water that's in the groundwater being sucked up by the plants and evaporating before it even gets to the lake. So here's my best estimate of groundwater. And Tom, that's what I was talking about. I've got sort of two estimates of groundwater now, or in terms of phosphorus. So now, if you look at Sherry's numbers, these are very close to what she was saying. With this hydrologic balance, I'm a little bit lower than that. But I do have the variability, and I think probably groundwater, Sherry's a long-term average model. This is what I think was over the last couple of years, and that's sort of following a couple of dry years, because when we started the project, it was a pretty dry period. But they're still pretty close. Okay, so this is telling us that groundwater, now if you put that in terms of the overall kind of thing, groundwater is coming in at about 17 to 23% of the Clam River. So it's not trivial. It's a fairly high input. And this is actually very close to what Gleck came up with before. So now, this is where that number I showed you before, total groundwater is putting in 327 kilograms. Now, if we use that change in the weights in terms of that season where I don't use the numbers in July, but use the spring and the fall more to get to that, that would increase that to 437. So when you look at this, groundwater is maybe a little bit more important than what I'll tell you about. Okay. So now when we put that all together, what we have is a hydrologic budget on this side. That's trying to put all these things together. I think you're asking this. So if you look at that, Clam River's putting in about 70% of the water, and groundwater is about 12, atmosphere rainfall, snowfall, about 14%. And almost everything is either leaving Torch River or through evaporation. And generally, evaporation comes very close to precipitation. And if you look at that, those two are pretty close. Okay. Now, but again, what this is telling you is that Clam River is the major source of water to the lake. Not terribly surprising. Okay. So now with that information, let's go to the phosphorus budget. So now the phosphorus budget says the P input to the lake. Really what I'm going to try and do is add concentrations to those flows. And so P input to the lake is what's coming in from the monitored inflows, Clam, Spencer, okay. The unmonitored, which would be Eastport, Wilkinson, Agamemnon, all the other nearshore areas. Precipitation, groundwater coming in. Normally that's a net groundwater coming in, but it's almost net and total are about the same. But we really want the groundwater coming in. Septic systems, the lake and land use around there, and finally internal. But I've showed you that internal is pretty close to zero. So I went through all of those this morning. We have an estimate for all those. And if we put those all together, this is what we come up with for the phosphorus budget for the lake. That's the water budget. And put the concentrations to it. And here's our phosphorus budget. So if you look at this, the Clam River is still the #1 source. About 57% of the phosphorus is coming in through the Clam River. Septic is about 20. Now with a lot of these things, you know, if we want to put air bars on there, you could see like, okay, that E sub S and there has a little bit of a noise in it. Groundwater, all of a sudden that could be give or take a little bit. But overall, this is my best estimate. And from there we can refine it and try to put air bars on it. But if you put that all together, we end up with 3,775 kilograms coming in per year. And that's the average of 24, 25. Okay. Now, if you look at this, here's our phosphorus budget. And again, if you look at it in detail, we put a lot of effort into Spencer. Only put in about 2% of the phosphorus. But it was interesting because we used that to get to other nearshore areas. So it is contributing some. Okay. So the two big ones, the Clam River and septic systems. And septic systems, depending on which way you want to go with that, might be a little bit more, a little bit less than that. Now, what I've set up to now is that this study is very similar to the GLEC study. And so what I wanted to do then was to look at this GLEC study and see if all this information we have makes us think different about Torch Lake. Okay, so here's the amount from our study. It says 457,000. GLEC study says 359. So there is less water, more water now, less water than before. Okay. But they were in a little bit drier period. So maybe it's not as bad as that makes it look like. Okay. Now we put that together with phosphorus. Even though we have more water, we got quite a bit less phosphorus coming in. So we estimate 37.7 and GLEC estimated about 4,800. So quite a bit more. Okay. So now if we go into how does the hydrologic compare, like I was saying, it looks like very similar overall. The Clam River is higher in ours, and so is rainfall. Those are the two biggies. Now, what is the Clam River flows? Why is it so much, why the Clam River flows so much higher now than it was before? Well, when the GLEC did their study, they only had point measurements of flow into the Clam River. And they did it during fairly low periods, and they knew it. And they said, okay, we got to adjust our numbers. So what they did is they looked for a gauge that they could correlate with. And when they correlated it, they picked the Sturgeon River, a little bit northeast of here. And they came up with this equation, but it was only based on 12 measurements. Okay. What I did is I went through and I actually looked at that same relationship, only now I have lots of measurements. And I compared all the months, 35 separate months, to try to see what that relationship would be if I did it, or if they had more data, what they would have got. So I did that same thing, plotted them up and so forth, and instead of being 1.28, I get 1.65. So if GLEC would have done this with more data, either they instead of having 12, they took a lot more measurements, they would have found out that they probably should have beefed the water budget up a little bit there. And that's about 29, 27, got 29, it's either 29 or 27% more flow if you would have had more data to come up with that relationship. The other thing is precipitation. I told you it was a dry period. If you look at that data, it was a dry period compared to now. And I'm trying to adjust for all those kind of things. But what they did is, again, they didn't have a rain gauge out here, so they picked the nearest thing that they could with good data, they thought was good data, which was Traverse City. They pulled out Traverse City and looked at it for those 12 months that they had, and this is where they plot up if you plot it up. So I estimate based on my data, it should have been about 0.68 or whatever that comes across. They had 0.55. Now that they used real data. In fact, I reproduced this, and that's what Traverse City said, but it was quite a bit different than here. Based on our continuous data set here, it should have been way up here. So there's quite a bit difference that they did the best they could, but Traverse City was extremely low. Why it was low, I don't know. So anyhow, I think they biased how much rainfall came down on the river or on the lake. Okay. So it was a dry period, but not that dry. Okay. So what I want to do then is what's the implications for this? Well, if you put just the water part, well, based on their numbers, you would have said that the water goes through here. It takes about 9 years to replace all the water. Based on higher volumes that I have, would be about 7 years. Part of that's due to a drier period they're looking at, and part of it was due to these extrapolation methods. Okay. But with that, they would have said that as we go through this, our numbers should have gone, our nutrients, the nutrient inputs should go up by about 27%. From our period would have been up 27% because we have more water, we should have more nutrients. But when we look at that, what we see is we actually have a lot less phosphorus coming in. If you look at it, it's 375 now, and back then they had 4852. So if we would have had that, you would expect that the more recent loading would have been higher than theirs because we have more water. So what's going on? What's the loading? Why is the P loading so much higher than the GLEC study? And that's even after I added septic systems and nearshore, and those weren't even included in their numbers. Okay, you could sort of argue that our septic is supposed to include groundwater and that, but we tried to separate those two out, and we tried to add septic in the way it should. So it really should be in addition to it. Okay, so if we look at that, really what it comes down to is the concentrations. If we look at these and blow them up, okay, look at the concentrations. The Clam River measured 0.005. We're measuring 0.006 today. Yeah, the same number. Okay. Spencer Creek, they measured 32. We very seldom got a number that high. In fact, we got 19. Okay. So that, normally you would argue that if somebody's going out and sampling a small stream, you're not sampling during the high flow events like we did. We bent over backwards to get the high flow events. That should have been the higher concentrations. So maybe something changed a little bit. The lab's still the same, but they got had a higher concentration. Maybe all the work that people are doing in terms of management is working over there. Other minor, they try to come up with an extrapolation technique with some samples. We really sampled the crap out of those little streams. We had people going out there monthly trying to get that. And we very seldom, like they have 23, our highest one in all our measurements was 31, and our average is 6. Okay. But the big ones that come in, precipitation, based on, they actually put out pans and they're trying to measure it. And they came out with a concentration of 42, 0.042. We came up with 0.003. Huge difference. Now, it's hard to say exactly what it is. I'd like to, you can always blame somebody for being too dirty. And when the two Toms went out and they're collecting data, they could have contaminated the sample, but you can't contaminate it to make it cleaner. So it's just that it seems that, part of that there was a decrease. I said that a nearby site went down 50%. Well, this one went down a factor of 15. Groundwater, we measured 6. Back then, they did a lot of sampling on this, and they came up with 32. So that's where the differences in a lot of these things comes out in the concentrations. Okay. All right. So when we look at this, now, back then when GLEC was looking at this, they tried to say, this is how much was coming in, 4852, and this is how much was leaving, very little. And there's a couple of kind of issues there. One is they overestimate a lot of the inputs. I try to show you they did their best trying to extrapolate it. If I had less data, I would have done the same thing. But the outflow, when it was measured, they really didn't have a gauge there. So they went through and that whole budget I did, they did the same thing. But because of some numbers were different, they came out with quite a bit difference in the Torch River. And their load leaving was only 830. So when you look at that, that's 83% deposition in the lake. Okay. Now when we do it, you look at how much, and we measured inflow, the concentration, outflow, and the concentration. We estimate instead of being 830, we got a lot more phosphorus leaving the lake, a whole lot more. And in fact, it looks like there's only 40% being retained in the lake. So it gives you a better idea. Fred and I have had different discussions, and it's like, well, where's all this phosphorus? Where's all this deposition? Well, we don't have as much as we thought was being deposited in the lake. Okay. Now, what are all this new budget and we compute the mass of phosphorus in it? It gives you different ideas on how the lake works. Now I'm going to go through a little bit of math. So if you don't follow the math, just try to get the concepts of it. Now, if we look at the mass of Dan, this is your idea in the first place. So when we look at this and we look at the mass of phosphorus in the lake, this is how much, if you took the volume and all these concentrations and put it all together, this is how much phosphorus is in Torch Lake. It goes up from 5,000 up to 20,000, comes down, up. And so that phosphorus is going up. This is over a couple of years. The mass of phosphorus in the water changes pretty dramatically, especially when you consider we're only putting in 3,700 kilograms per year, and we're going from 5,000 to 20,000. That's over a few months. The amount of phosphorus in the water part of it can go 15,000. That's 5 years worth of loading that it can change over a couple months. Okay. Okay, double it. Okay. Okay. Again, I could change this and say this is all in pounds and just forget it, but the idea is that the fluctuations in the lake are way more than what's coming in. And so what we want to do then is so we got some internal sources coming through here, and then we got some deposition going on. And what I want to do then is to try to figure out how much deposition of that phosphorus is, how much coming from internal sources. I told you that it wasn't coming up from that deep water, but it doesn't mean it's not coming up from all over in the lake. And also being deposited. Now, in the GLEC study and several other people, you would believe that calcium carbonate is the main way that phosphorus is being removed from the system. Okay. All right, that's just the standing belief, at least that I've understood. Okay, so what we want to do then is just take 2 points. What's going on between this point here, which is, I think, I'll have to go, I think that's like December and March. So there's a lot going on during when the lake was frozen. So when you look at that, what I wanted to do is the amount of deposition in the lake, you can look at that just by the difference in there, right? So if I have 1,000, I end up with 500, 500 is deposited. But you have to look at how much is coming in versus going out and add that little bit. But like I said, 3775 is small, so it's gonna have a small effect. So if we do that, put it into a little bit of math, and then look at the changes between December and March, and go through the change in mass plus the inputs outside. What you end up with is, I can get, like I said, it's almost a change in storage because the mass is pretty small, but I can figure out how much is being deposited in the lake, okay? So what I did is I went through and did that between every sampling period, trying to figure out when phosphorus is being deposited in the lake. And so when you look at this, what it is that anything below 0 are internal sources. Anything above 0 means that it's being deposited in the bottom of the lake or into the bottom sediments. It's just getting out of the water column. Okay. Now the interesting thing here is that look at when deposition occurs. This is November through May. November through May. Here's a little bit of the middle of the summer. But the big deposition events are occurring sort of in that fall-winter period. That's not calcium carbonate precipitating. That's just the algae dying and falling to the bottom and so forth. So calcium carbonate, does it occur? You bet. You can go out there and see the plume, you can see the bottom up there. You can see changing Secchi depth, but there's other things happening out here. So there's a lot of deposition occurring on top of the calcium carbonate. Okay. So it just gives you a different idea of how Torch Lake works. Okay. So first of all, I said there's little internal loading. We had some that first year. I could see that in that difference in phosphorus concentrations as it went through the summer. That increased. That was that year, but it didn't really occur after that, too much of that. But most of the sedimentation, like I said, is happening in that fall to spring period. Okay. Now, when we go in there, okay, here's the number that if you go through all the calculations from the GLEX study, it came up to 4852. But I said some of those flows were overestimated or underestimated, and the concentrations were different. So what I try to do is to go through each one of these things and change them based on a new relationship with that river in other ways. So I changed the flows. Sometimes I kept it similar. Like for Spencer, I said, okay, Spencer's probably the same as it is today. Maybe I should make a little bit of adjustment. But the big changes were these concentrations. So like if you look at this, so I kept their concentration. Whatever they came up with looked good to me, so I wasn't going to change it. If you get to like atmospheric deposition, they had 42. I changed it to 0.005. So it's higher than we had by that 38%. Okay? And so I went through and tried to change everything. And the bottom line is from that whole thing, I think it was overestimated a number of years ago. Instead of being 4852, I think it's closer to about 2,700. And that's about it looks, depending on which way you go, if you were to say this is reality, then that's an increase of 75%. So I think that the loads back then were not as high as what they thought they were. Okay, and that gets back to that idea of how much is being deposited. There just wasn't that much coming in. So much less retention in lake. I think it was about 38 instead of 83%. Calcium carbonate is less important than previously thought. I'm not saying it's not a permanent kind of way for this phosphorus to be removed from the system, but on that short term, the dying and settling of plankton is probably more important. But now since we have that smaller number, you can see that small changes in the phosphorus load are even more important. So when we're talking about septic or this, the changes that we're seeing can be pretty dramatic because we're only playing with a small number. So the take-home message out of all this, Clam River is the main source of water and phosphorus to Torch Lake, even more than previously thought. Groundwater and atmospheric inputs are less important. But depending on how you define groundwater, because I'm also saying that septic is important. So that comes in there. And less phosphorus than previously thought is being retained in the lake. And finally, the amount of water in Torch was underestimated, but okay. Now, now that we have a phosphorus budget and we have other kinds of things, we can look at this whole process of going from a oligotrophic lake to a eutrophic lake. And what we do know, or what we need now, are new response curves. Black had some of those in their study. And what we want to do now is to reconstruct sort of a loading versus how the lake should look like. So we need the response curves. And what a response curve really is just saying, okay, here we are today at 0. If we increase loading, what's phosphorus going to do? If we decrease, and that's what we want to do, is come up with response curve. So the way different than a lot of other studies, we take this entire load, couple empirical models. It's very simple. These relationships are driven off of a number of lakes. So we start off with these models. The model that I like to use for the Midwest is the Canfield-Bachmann model, and I'll show you that. And use that trophic state index to try to translate phosphorus into chlorophyll into Secchi. Okay. And also have a model for chlorophyll. So what is that Canfield-Bachmann model? This is the whole thing, very simple. It just says phosphorus concentration is a function of the loading to the lake divided by the loading to the lake and its residence, its depth, and its residence time. So it's a very simple model. As the loading goes up, concentrations go up. But if the water is going through real fast, it sort of dumbs things down, or it actually will make it respond quicker. Okay. So when we look at that, first of all, we just try to show you that the model works. We ran it. The measured value is 0.0043. That's the average summertime concentration in the lake, and the model said it was something very close to that. So the model said 0.0038, we measured 0.0043, really close, but anything we do, we want to correct for that little bias. So then we basically go through and change the loading and incrementally, and we get this curve. And all that's saying then is that if we add phosphorus to the system, it's going to degrade. The phosphorus will go up. If we remove phosphorus from the inputs, it'll go down. Now, with everything I'm saying, I'm not adding biology into this. Biology can, we'll let Jan talk about that in a second. Biology can throw a wrench into some of these things. So now, how do we compare nutrient concentrations for chlorophyll and Secchi depth? Well, it's going to go back to this. So if I say that this phosphorus changed from 20 to 30, I compute a TSI, then take the TSI equations and sort of run the math in reverse and say, what would a chlorophyll of that equal? Okay. So the idea is predict phosphorus using the Canfield-Bachmann, then convert this to a TSI, then take that TSI and convert it to chlorophyll. So it's sort of bouncing around assuming that, but I showed you those TSI values are a little bit different. Chlorophyll is lower, so we're going to assume that as phosphorus changes, the biology doesn't know it. But in this lake, we've already shown that you have to be a little concerned about that, because if we change the phosphorus and it goes up, it might switch the whole system a little bit. Okay, we'll talk about that in a few seconds. Okay, so anyhow, we start off with our phosphorus one. Then we go through and say, okay, we convert each one of those values on that whole curve to a TSI value, then flip it in reverse, and this is what we get. And for chlorophyll, I told you that it was a bias. I showed you that the two had different. And so what we want to do is adjust these values down. Okay, these are all still very low, this maximum concentration is only 1 microgram per liter, but we still want to adjust for those. So if we do that, we have a TSI model, and then we have a model that's independent of that. But in general, again, as phosphorus increases, chlorophyll goes up, and as phosphorus decreases, it'll go down. Now that's assuming, again, normally I would never say this, but that's assuming that we still have a benthic community that's driving a lot of things, and the open water community doesn't change. Now, in reality, once we get up above some number here, we're going to see a really change in things, because everything we're going to talk about the rest of this afternoon is probably going to would disappear. Would we have GBA? Probably not. As you increase the phosphorus concentration, the open water algal species would probably take over again, and all of a sudden things would change. So you have to be a little bit careful on the far end of that. Then, wanted to do that for water clarity. Again, we do that translation. And now for any phosphorus decrease, we can get an idea of what kind of things. So when we're all said and done, now we got the trophic state indices, or that the response in all of those, and we can say if we added more phosphorus to the system, what would happen? And that's just saying that this is a very responsive lake. We don't have much phosphorus coming into it, and these small percent changes can have a fairly large effect. Okay. So one of the things I wanted to do with this, now that we have the response curves, go, okay, what do I think the phosphorus concentration would have been like back in 2005? Okay, we really don't have, we have their measurements, and so what I want to do is just plug them into my models. So if we go through there and say, okay, this is a change in X percent, we go through, if we had the GLEC data alone and use their loading, phosphorus concentrations in the lake should go up to about 5 or 6. Based on this new model, it would drop a little bit. So it gives you an idea of what, I don't even know what the real numbers are. I'll have to look at that. But this is just sort of saying we can use this model to try to reproduce stuff in the past or in the future. Okay. So take-home message, the Canfield-Bachmann model worked very well for Torch Lake. Water quality should be very responsive to small changes in loading. And that's going to be really important for all this, is that we don't want that phosphorus loading to change. Now, I won't even get into it, Trish. In 2005, concentration should have been a little bit less than they are currently. Okay. So with that, I think I'll open it up for any questions that we have.
So the settling of phosphorus removal does settle, to less than we once had
Yeah.
predicted.
It's definitely less, but what it is that they're settling at different times of the year. Yep.
Yeah, so the phosphorus settling occurring outside of the temperature period that you would have carbonate saturation. What's the mechanism, do you think? Is it that 75% is particulate and it's the lake during that time is not stratified or mixing, so it just settles out? Or what is the mechanism that
I just think it's simply the phytoplankton, zooplankton are dying.
they just
and
die and float and sink to the bottom?
And then, in terms of, there's a lot of recycling with that stuff decomposing and coming back up. So you've seen those big changes. What's that?
Let me give that to Trish. We need to hear your question.
Dale, you're showing us that the phytoplankton is so low,
Yeah.
I just can't see that much deposition of phosphorus.
Right. We don't really have a real breakdown. We do have those concentrations. Everything I'm showing is based on the phosphorus concentrations we measured in the lake. So as you're watching it, it is increasing. Our concentrations of phytoplankton and zooplankton are only at those point measurements. If you added up all the pieces, you'd have to go down and actually try to break that phosphorus down into all the parts on every time period. But all we have is the total phosphorus at 5-6 depths, and we integrated that over the water column. So,
But you did indicate about 75% of it is particulate phosphorus or other than dissolved phosphorus. When you had the concentration, I thought it was.
typically, yeah.
Right.
Almost
So
at-
that
so 3/4 of the
particulate
time.
By definition, is simple,
Yeah.
even if it's not.
Right.
Not been uptaken by biology.
Okay,
But this is always a problem when you're looking at it. Like, you do see these massive changes, and I think Dan was one of the first ones that brought up. It says, you're looking at this and it's going through, and the only thing I did is I put the numbers with the areas to get a mass out of it. And so when we're changing this, is when you're seeing it consistently year after year, that's when you start to look at something. And typically we see that big change in those concentrations during that fall period.
you have a follow-up question or are you good?
No.
Okay.
Dale, going back to your to the model that you had, it's one of the things that I note that I didn't see was that in reality you're saying small changes in phosphorus, but if you look at that the slope of the change curve, the model curve there, if you were to superimpose the uncertainty of the response curve to say a 5% change in phosphorus, it seems to me that becomes a wash. And then one of the ways, and the only reason I have to ask if you could validate that is if you look at where you're sampling the actual phosphorus level in the body of the water. Obviously, it doesn't include the stuff that's being deposited by the biomass. But then you have that versus the algae, you have that versus the Seichi disc itself. That would at least give you an uncertainty envelope around the actual responsiveness in a small change. So that would be asking the question is, what's the uncertainty of a change of plus or minus 5%? Obviously, if we say a plus or minus 50%, I think we'd all agree there's going to be a big change.
Right. Yeah, that's always a problem when you're playing with these games, especially when you got a 7-year residence time. Okay, it's coming in. So I only have 2 years of data, possibly 3, to do something like that. And you could say, could I run those years with the data we have to see if it works? And usually that residence time comes in. So when I like to run a model, I'd run like the 2004 and 5 together and do it then, or run it 5 years here, 5 years there. And a lot of my lakes that I work on have 30 years of data, and I can do that. Here you just can't. And so it's just sort of saying, the bottom line here is adding phosphorus is bad. At least it's bad. Problem is I know too much. Adding phosphorus is bad. I'll leave it at that.
If there's no more questions, we're going to move on to Dr. Jan Stevenson. Thank you, Jan.
Right here. There you go. Oh, thanks.
Can everybody hear me? This close, that close, this close. Okay, so I'm going to talk about recent data, primarily the 20 Lake survey for most of you that are familiar, for people that are familiar with that, you know what it is. How many people haven't heard me talk or don't know about golden brown algae or? Yeah. Okay, so you're right, Mary Ellen was wrong. I didn't need all these introduction slides. So I'm gonna kind of move through that. But first I do want to thank the people that have helped throughout all of this, and particularly, I haven't added Mary Ellen to the list. Mary Ellen, my wife, has been out sampling constantly with me. Late nights getting back, and not so much early morning starting, but late nights getting back. So thanks, Mary. And that's the problem. A bunch of algae growing on the bottom. It's a thick calcareous mat. It's made up of diatoms, golden brown algae with glass cell walls. They're incredible under the microscope. And cyanobacteria, which aren't nearly as much fun taxonomically to deal with. And we've tested a bunch of hypotheses. And recently, in recent years, we've been working on the idea of, is it increase or decrease in phosphorus? Phosphorus being like the most likely limiting nutrient. And this fits into the broader project with USGS. So today, I'm going to talk about, Rick asked me to add environmental monitoring onto this presentation. And I was going to talk about next steps first, so then I can get to the data and we can talk about data after that. Really quickly, I've worked with in environmental monitoring and assessment with the EPA, with the states, with all kinds of groups, with the National Lakes Assessment, Westland Assessment, Stream Assessment. It's a long conversation. So it really, what you want to do depends on your goals and your budget. You have to narrow things down. But considering what you're doing today, really cutting to the chase, you need a lot more samples. You need a lot more samples in time. You need a lot more samples in space, those being water chemistry samples as well as biological samples, because the biology, I think you'll see a little bit of it today. It's really, some of the, I mean, different biological signals give you different information, but the diatoms tell you about water chemistry conditions. Let's leave it at that. So putting together this project is not trivial. I'm going to write about it a bit in the report that I write up, but I'm going to leave it there unless you have specific questions to talk about a really big conversation. Is that okay, Rick? Okay. All right, so now I'm going to talk about next steps, which is I've still got a lot of data to analyze, or samples to analyze and data to process that I'll be doing this summer, but I'm planning to wrap up the key parts of this for a December report. And in that report, we'll have a lot of the key parts of all of the projects that we've run in the last 6 or 7 years. Look how fast this transition is. And today I'm going to talk about those two, and mostly the one on the top. If I get the pointer is the top one? Nope, middle one. There we go. Mostly the 20 Lake survey, because that we sampled a lot last year, and I've gotten a lot of the water chemistry or the sediment chemistries back from Florida International University. And there's some interesting patterns that were hinted at when I've talked about it before, but they are crystal, in my mind, they are crystal clear now. So, and I'd like to give you a heads up so you can think about what's going to happen during the presentation. But so I'm going to review the 20 Lake survey. We basically doubled the number of lakes or lake basins that I've gone to. There are really clear relationships between GBA and low phosphorus conditions, high GBA in low phosphorus lakes. And there's signs that you need enough nitrogen in the lakes for the GBA to grow. There are some low nitrogen lakes in northern Michigan. I'm only going to talk about one slide on that experiment. And the experiments in general
confirm this, that if you add phosphorus, you lose the calcium carbonate, you get different kinds of algae growing. They love phosphorus, you get lots of algae, but you do not get a calcareous algal mat. And in fact, like in the Everglades, where there's a similar kind of assemblage of algae, uh, um, you lose the calcium carbonate with more phosphorus. There are actually hints in the experiments that elevating phosphorus increases the amount of calcium carbonate precipitated and affects the species to stimulate more GBA species, which is really fun biology, but probably will show up in the report versus the conversation today. So the data to support that comes from the 20 Lake survey that we completed across northern Michigan, basically with phosphorus concentrations ranging from 3 to 9. So measured phosphorus concentration, well, Charlevoix is often 2. So measured total phosphorus concentrations in the lake in the spring range from 2 to 9. 9's not very high. And the idea was to look across that gradient with higher ranges in phosphorus concentrations than just within Torch Lake. So I'm looking for these, using this survey to find the patterns. So we went out in the boat, used a sampler, this just think that I had stuff in the garage to make one. And then at each site scooped up sediments off the bottom and got a mat sample, if I could distinguish one, put it in a Petri dish and then froze it for later analysis and put spoonfuls of sediment into a WorldPack bag. So I've got sediment and mat samples from all of these. This year we sampled Douglas, Walloon, the 3 different basins, Crystal, North Leelanau, South Leelanau, and the South Arm of Lake Charlevoix. I went back to Elk, Bel Air, and North Charlevoix for reasons that we can talk about but aren't really important. And in each of these, we sampled 2 sites. One, I would look at maps and figure out where there's low riparian land use and try to hit a place where I'd expect low groundwater nutrients coming in. And the other in a more active riparian level area, and sampled both a mat and gray matter if the mat was present, and got 2 to 3 samples per lake. So for this presentation, I've estimated the amount of algal biomass visually. There are going to be some more rigorous measurements in the future. And I've characterized the diatom species composition of these mats. I've chosen those 2 things because I know the sensitivity of the species to the change, and the biomass is really a direct measure of what we're concerned about, is how much calcareous algae or some kind of algae is on the bottom. And then the water chemistry, there is no mat chemistry yet because some of the mats are so small, I don't know how much of the mat that I'll give up to go to Florida International University to have it analyzed, and how much I want to keep to look at algae in them to get the algal signal out of as many mats as I could find. I think there's only one lake I couldn't find some kind of film or something on the bottom and distinguish it and scrape it off and put it in a Petri dish. Trying to think that mat's probably like the most sensitive part versus the sediment that comes up. It's a lot of sand and calcareous material and maybe mud, depending upon where you are, and it's just scooping it out and tossing it in a WorldPack bag and sending it to them. So it's the algae is all mixed up in that sediment. So we've got the water chemistry and the sediment chemistry that was done by Florida International University. Florida International University is the university that does all of the water chemistry for the Everglades and throughout the Caribbean. So they're really good. Okay, so the first thing, how much algae is there? And I did that by looking at the videos of sampling on the bottom, pictures of what came up in the plastic container, and then I've got the mats.
actually back in the lab. So when I took those out, I kind of characterized how thick are the mats, how calcareous are they, and then yeah, how thick are they, how much and how calcareous are they, and basically came up with a scale that if it's above 15, these are thick calcareous mats. These are what have been characterized in Torch and only a few other places. About greater than and less than 15, about 10 or more, they're calcareous in nature, but they're not really very thick. And then about below that, you pretty much have goo and different amounts of goo, so less than 10. So there was a scheme to the plan. So Big Glen would be kind of like goo. It had algae here, but this is all pretty much sand with very little calcareous material in it. This is Little Traverse Bay, one sample of 3 where there was a really pretty thick algal mat, almost as thick as some of the really thick mats that occur in Gourley. So this was, so Charlevoix was a 15, Torch was a 18, Elk was a 19. Elk had really thick mats consistently, you know, and then we get down to, that was an 11. Or I'm sorry, 16. Then I looked at diatom species composition and it came up with a simple metric based on a set of species that we find in the mats. Just looking at the relative abundance of those. When I look across the slide, what proportion of those, what percentage of those are these species that are characteristic of the thick mats? And this is the relationship between the amount of mass, my mass rank, and the species composition match, which is actually a pretty good biological relationship. So we start there. Is there a relationship between my 2 indicators of how much golden brown algae should be there? And then I'm going to relate those things to the water chemistry and the sediment chemistry. The sediment chemistry is, it measure phosphorus, nitrogen, total carbon, and then an inorganic carbon that then can be distinguished from organic carbon. They incinerate the sample, so there's no organic carbon left, and then they analyze it for carbon, so that's the inorganic carbon. That inorganic carbon are carbonates, almost all carbonates. So that's the indication of calcium carbonate in the sample, is the inorganic carbon, which I won't talk about a lot today, but it's mostly phosphorus and nitrogen that I'm going to be talking about, the water chemistry and phosphorus to carbon is going to be a big thing in the presentation. So I'm going to go through a bunch of different relationships between algal indicators and phosphorus, and then algal indicators and nitrogen to give you a sense of why I think both phosphorus and nitrogen are regulating these assemblages, the mats. This is, start with the best relationship and then go back and tease it all out you guys see? Tease it all out, so I'm confident that the best relationships is the good. Actually, this isn't quite the best, but it's really close. So here we've got a nice relationship between the species that are there, which are, as I mentioned, really sensitive indicators of water quality change in the environment that they live in, like a mat, and the increase in sediment to phosphorus to carbon ratio. So the more phosphorus, the lower GBA. In fact, the higher GBAs are down in this range of, just to give you a hint of what you're going to see next, down in this range of sediment phosphorus. So now we'll kind of stepwise go through an analysis of total phosphorus to different measures of the the mass and species composition. Here's the GBA mass rank. Here's total phosphorus. There actually is a negative statistical relationship between total phosphorus and the amount of GBA that's there. So we've got Charlevoix, Elk, Torch. Actually, to highlight Torch, I used the range of the best, some of the better mats, not the best, thick mats, and what we might see at Hayawenta North typically. So Torch is underestimated in a lot of these figures because I chose Hayawenta North as to give me a sense of how far off are we. So and up at the upper end, there's places like Douglas Lake, and I think this is Little Glen, Big Glen, and other things. So down here is a group of, no, actually this is, I think, Little Glen. Trying to remember which one's which, but anyway, this is a bunch of low nutrient, I'm sorry, not low nutrient. This is a bunch of samples or lakes that we're concerned, I'm concerned about in this relationship. Why are they down there? So in the next few slides, we'll be going through some of that. This one is actually, oh good, I marked these. Northwest Walloon, which was the northwest corner of Walloon. I'm sorry, I'm not on the mic very well, but this is Northwest Walloon. This is Northeast Walloon, which the turbidity in these places was really high, and you're going to see that sediment phosphorus was really high. And this is Crystal, which was a new lake to add to it that was a beautiful lake. And so to understand these things better, I came up with a lake, I just, ranked lake phosphorus concentrations, and then did box plots to kind of look at who's sticking out and what kind of makes sense. So I'm highlighting a couple of places like, this is Burt, if I remember correctly. This is Little Traverse. This is North Charlevoix. No, this is Skegmog, good. This is Skegmog, which was interesting as a really low phosphorus, but I was not seeing calcareous algomats in Skegmog where I sampled. So it's interesting that this would be relatively low GBA if the phosphorus is indeed this low. Other measures of phosphorus are going to move it up that scale, other than measured water column phosphorus. Yep, that's where I want to stop there. So I'm basically doing a residual analysis based on the lakes and what I know about those lakes and why are they deviating from this pattern. All right. So this is the species index, again, negatively related to total phosphorus with some outliers. Mapping it, we now have these two Little Traverse, and that indicate they've got a lot of GBA species there, but they've got the water column phosphorus is relatively high compared to the other lakes. Douglas is still the highest, around 9. Here's Burt, which is going to move back here. Little Traverse is going to move all the way down here when we get to some other measures of phosphorus. All right, so here's now we're measuring sediment phosphorus to carbon ratios, and the relationships get a lot better. Things are moved back and forth on the scale, indicating that water column phosphorus concentrations, when you match it up to biological responses, are not as accurate as the sediment phosphorus concentrations. And that makes sense for a variety of reasons. Let's go on with these responses. Here's now where Burt Lake is, kind of in the middle, and Little Traverse Lake, based on lake sediment phosphorus, the carbon ratios is here. So we've got one outlier here with Northwest Walloon, the Northwest Walloon Basin, on a pretty good relationship. That's difficult to explain, and all I could tell you is that in a moderate phosphorus concentration lake, last summer when we measured, when we went there, you couldn't see, it had a Secchi disc. If I take a Secchi disc, I couldn't see the sampler more than 6 feet down in the water, and I'm sampling 10 feet. So we were sampling blind. We had no idea what we were pulling up. For some reason, last summer, it was really turbid, and there might be other issues associated with it. So now we're starting to really kind of resolve a phosphorus to GBA relationship when we're looking at the sediment phosphorus concentrations. So here the species again in a scatter plot, and here is species again in a box plot, and it's almost perfectly linear. A perfect relationship between species responses to phosphorus in the sediments of these lakes. And Little Traverse down here with high high thick mats is now oriented down here at the lower end of the graph. Northwest Walloon comes up because the species are there, but the mats weren't there. So the water chemistry is right. So something else is constraining it from being high. And that habitat, I'm thinking it was turbidity that summer. But all right, now let's get to something. How am I doing on time? How am I doing on time?
You're doing fine. You've got another 20 minutes.
Okay, I can do that. I can do this. So I wanted, we're all fascinated with criteria and figured out, okay, at what level does this happen? So if we pick the phosphorus mass to sediment phosphorus carbon ratio, basically around 4. When the sediment phosphorus to carbon ratio is less than 4, so that's Burt Lake there, and Burt Lake was only just kind of calcareous. So really, the ones that are less than 3 might be better, but we'll pick 4 for this argument, and then relate it back to measured phosphorus in the water columns, and it's a pretty messy relationship. But if you draw a line through there, a sediment phosphorus concentration of 4 would actually equate, coincidentally, to a water column phosphorus concentration of 4. That's assuming that's a linear relationship. If it's not a linear relationship, where you can imagine there's a lag in sediment phosphorus increase with an increase of water column phosphorus, maybe not. But if there was, it would be about 6. So I'm just doing a little sensitivity analysis. I'm trying to figure out at what level are the golden brown algal assemblages developing. Now, if we look at the mass ranks and actually correct for sediment phosphorus, basically all of these lakes come down to below that 4 threshold. And we've still got these lakes that are constrained to this area, which is Crystal, Northeast Walloon, and Northwest Walloon, which the phosphorus just seems to be more phosphorus there. Now I'm going to talk about nitrogen, just very briefly. Why nitrogen? Well, last year when I was talking, the Glen Lakes had reasonable amounts of phosphorus, kind of on the low end, and we would expect it. I expected to see thick mats down in the Glen Lakes, especially in talking to the regional biologist, thinking there'd be pretty thick GBA there. And I also knew I was going to be going down to Crystal, so all 3 of these then, we did not do Platte. All 3 of these then are in the sand dunes along the coast. It's really a different geology than over here. And when looking at the Leelanau Conservancy water chemistry data, these lakes had no nitrogen. I mean, they were really low. It was like 50, and they don't measure total nitrogen, so I'm going to work around with that with a fudge factor. They only measure nitrate. But when you've got a nitrate of like 40, that's low for algae. That's very low. So here we go. So the nitrite concentration, I think this is Little Glen, is 34. The nitrite concentration in Big Glen is 84. Now, this is actually a positive relationship between nitrate and algae, despite these lakes down here that for different reasons don't have the GBA growing. So these nitrogen concentrations just seem like they're really low and might be low enough to also find no GBA in crystal. And it has pretty low phosphorus concentrations. Crystal has no nitrogen measurements that I can find. Now I need to get in touch with people at Crystal, but they have no nitrogen concentrations. This relationship would actually you'd expect maybe if nitrogen is stimulating GBA development, it's going to go up and then it's going to come down. But I'm pretty convinced that there's sufficiently low nitrogen in those lakes with their low phosphorus that the low nitrogen is constraining the growth of the GBA, the calcareous algal mats. So the species index, I'm not sure why I had that up there. That's right. It becomes really clear this almost perfect asymptotic relationship, except for a few of these lakes where actually they have relatively high phosphorus that is changing the potential for the GBA to grow based on the species index. It's pretty much what you'd expect, an asymptotic relationship with nitrate. So this is dealing with survey data, which is very messy and not mathematically generated. It's mathematically analyzed. Now, not far from here, over at the UMBS Biological Station, a number of years ago, one of my graduate students and I, Steve Ryer and I, worked a lot in these experimental streams. And we did a study of how nitrogen and phosphorus affect algal growth rate and the amount of algae that accumulates on clay tiles. So this is stream algae, not benthic algae. And we talked about low nitrogen being a problem for the development of the GBA and the potential that low nitrogen is limiting GBA in some of the northern Michigan lakes, or I talked about it. And this is the results from an article that we published as part of Steve's dissertation. This is maybe the sloppier of the two because growth rate is kind of hard. And chlorophyll A is actually the more translatable to the amount of mass that's there. So as inorganic nitrogen increases, basically it takes about 200 micrograms per liter to get up to a saturating growth rate. And below that, there's a really strong negative effect of nitrogen on algal growth and accumulation. So some of the lakes in northern Michigan have those low nitrogen concentrations where nitrogen could be limiting the GBA development. And that explains some of the residual error in the relationship between low phosphorus and high GBA. This was actually nitrate. This is dissolved inorganic nitrogen. Sorry. Yep, dissolved inorganic nitrogen. It was manipulated with nitrate. Okay. The one slide from the experiments that I thought that I consider really important. This is the inorganic nitrogen, the inorganic carbon fraction, the total carbon. It's our best indicator of calcium carbonate. This is the Frederickson project where we did in 2024, where I manipulated nitrogen, phosphorus, nitrogen and phosphorus. And then the Petri dish samples are samples of what natural was in the background. They were just samples of the short cores that I took of the mats. All of these over the 3 weeks that they were accumulating, the control is moving toward what this Petri dish sample was. It really looked like a nice calcareous algal mat. It just wasn't as thick and, and completely developed. But it's interesting that, that the phosphorus had so we saw other indicators that phosphorus was negatively affecting calcium carbonate precipitation in these mats in the experiments before. Here's actually the measure of calcium carbonate precipitation, how much calcium carbonate's in the mat. These started from sand with algae mixed in them. And over the 3-week time period, this developed into a calcareous algal mat. If I add nitrogen, you actually get more calcium carbonate precipitated. So for those of us that are kind of familiar with the variability around one anecdote, and it's only an anecdote, is we know how much GBA there was in the Gorley Bay, and kind of always going, why is there so much GBA in Gorley Bay? Phosphorus isn't any higher, and we did studies there. If you give them more nitrogen, and there was lots of nitrogen in the groundwater in Gorley Bay, in the measures that TLA made, that could be stimulating the GBA development and why it's so rich there. This fits the Everglades, where there's calcareous algal mats. These are phosphorus limited systems. These calcareous algal mats develop in relatively low circumneutral pHs. They find the calcium in the water column and form on the sides of plant stems, float up to the top, continue to grow out. And when you add phosphorus, these mats disappear. If you add only phosphorus, these mats disappear. So the 10 microgram per liter total phosphorus criterion for the Everglades was based on experiments and surveys that showed that that's what happened. So these are phosphorus limited systems. You get, at low phosphorus, you get more calcium carbonate precipitated, and that calcium carbonate armors the algae that grows so that when it grows, it doesn't go away. It doesn't sediment out of the water column with the rain or some other thing for the floating algae. And for the algae on the bottom of torch, fish moving around a bioturbation by waves or other things on the bottom. That's calcium carbonate is armoring that mat so that when the algae grow, they persist through time and accumulate over a 3-4 week period. In addition to the extensive literature that describes how calcium carbonate precipitation in these mats might be helping harvest phosphorus to stimulate and sustain the algal growth to form these thick mats. There's algae throughout those mats. So that's why I think phosphorus and nitrogen are both important. Low phosphorus is stimulating the GBA development. Low nitrogen constrains its development in a few of the systems up north here. I think long-term changes, the long-term decreases in phosphorus in the lake that are evident in data sets from the Tip of the Mitt Watershed Council. I reanalyzed Steve Hamilton's, or the data that Steve Hamilton has presented here, and talked to Steve. And the Leelanau Conservancy data shows a clear decrease and increase in all 5 lakes that they have, despite the slight amount. And the reason you can detect that in their data set is they've got lots of data. They have 5 or so measurements per summer. So you can get a nice average for each year throughout that long time period, and it goes down and it comes back up in recent times. MyCore has data that shows that crystal goes down. Actually, a report Phosphorus decreases are noted in a lot of northern U.S. lakes in the U.S. EPA's National Lakes Assessment, and then Sherry Fritz's paleo. The National Lakes Assessment data was also paleoecology that showed before human disturbance and to now, there have actually decreases in phosphorus in lakes. So with that, I'm bailing out. Yes.
The threshold of phosphorus, above which you don't get enough calcium carbonate deposition within the map or whatever, you don't have the GBA species emerge. But as you get lower in phosphorus, it doesn't. There's no effect. So the question would be, if we had more N, towards like, we have the potential for a lot more impact development than we already see.
I didn't study that. I don't know. I don't up in that range of N. I think you're at a point that you've saturated. Up at 250 micrograms per liter dissolved inorganic nitrogen, and assuming that ballpark half of the nitrogen in torch is half of the nitrogen in torch is dissolved, it's not going to make it any worse if you think golden brown algae mats are bad.
Just make sure I understand. What you're saying is that if the nitrate level in the water.
Here, I'm sorry.
If the nitrate level in the water column is below a certain threshold, even with low phosphorus, you're not going to see the same level of GBA proliferation or mat development or mat density and all that. There's a threshold of nitrate that's required along with the low phosphorus for that phenomena to happen.
Yes. Yes. Yeah. And then, yeah. Yes.
Just to change gears a little bit, it's still on the same thing. You're looking at two indices of GBA. You're looking at a GBA mass rank and a GBA species rank. If we went out, I'm trying to get some satellite things to look at that. Can I see either one of those with a satellite? Or is it? I can't see the species rank.
I see it. I see.
But can I see a GBA mass rank?
You would have trouble distinguishing non-GBA benthic algae, which is mostly diatoms, and GBA.
Okay.
So in torch, I'd argue over most of torch, that will work. And it'll be a very sensitive indicator that if indeed, as many people think, phosphorus is going back up in the lakes, of the decrease in GBA in torch. My guess is that'll take years because you just got to rinse out the species and the legacy. But I think satellite imagery would be great. I've talked to a bunch of people about it. Nobody's picked up the ball at Michigan State. And I don't know enough about it. And Art Hoodley and I were going to try to figure it out. We go, nah. But we see it, I see it clearly in Art's area photographs, which will be one of the things but.
Okay, with the satellites, we got two possibilities. Dave Hochschlag and Mike Sayer over at
That's great. I think I used the poo-poo satellite imagery, and then one day I was flying over Lake Erie, and I said, "Oh yeah, you can use satellites to figure this out." You know, it's color. You know, it's color.
That's what I was wondering about the.
Yeah. But distinguishing GBA from diatom-dominated benthic algae from the green algae too around the margins, and you'd really need a high-resolution imagery to get the green algae around the margins.
I just wanted to mention there's coming more available hyperspectral data, which I think will be fairly interesting to look at, especially if we see some seasonal variation in the coloration. It may get us a series of spikes, which release some positive identification. And I really like
Yeah.
to work with you in terms of knowing where you have identified
Yeah.
GBA and where you have not.
If you can get, even going back and get the historical satellite imagery with maybe Planet or something like that. Yeah, that matching that up with Art's photographs, and then me sampling and cruising around and then doing it seasonally. I mean, I think there are sufficient gradients there to develop a model to do that.
Jan?
I'd be amazed if not.
So maybe you're not there yet, but with all the curves, could you, and if not, if you can't, when would you be able to say, kind of like below this phosphorus range, we risk GBA, and unless nitrogen is such and such, and above this, we don't get GBA, but we get everything else. It's almost like if you're used to, and I know you're not, but like in a different context, there's things called operating envelopes where you say, as long as you run a piece of equipment or a plant in a certain area, you're safe, So I'm kind of like looking for where is the operating envelope
So that's
for Torch Lake with respect to nitrogen and phosphorus
my
quantitatively,
my
not-
environmental criteria world. That's the threshold and the in assimilative capacity, and that's there. I took a bunch of slides out. They're actually later in there to go into this a lot deeper, but here, I mean, really, it's 3. It's 3, 4 down in that. It's Torch. It's Torch. It's Elk. It's North Charlevoix. It's just a very few lakes. Bel Air has the capability. If you can, for some reason, I'm not finding thick mats around Bel Air, but I know historically they've been observed. But I'm sampling it deeper. And so I think 3 or 4 below that level, you're fine. Above that level, you have benthic algae, but it's not calcareous. And then probably up here at 9, that's when you have the phytoplankton starting to accumulate to high enough densities that it's.
That's phosphorus carbon ratio,
right? Yeah. Oops, sorry. Yeah. Yeah. That's.
We're measuring phosphorus out the middle or nitrogen out the middle.
So Dale's asking, should we be measuring sediment versus water column? Well, for benthic algae, it makes more sense than for phytoplankton, but for phytoplankton, the water column is more important. The problem is the water, as you were showing with the modeling and the deposition, that we go from a whole lot of phosphorus in the winter to boom, it just drops out. And and if you've looked at any of these long-term records of phosphorus, I think the last measurement in Torch was 14. And it's taken every 3 years. What are you going to do with a 14? I threw it out. I looked at kind of more of a consistent average. That might have been a bad year for Torch, but it wasn't during the time that I sampled it. Sediment phosphorus, the biological indicators integrate over space and time. Sediment phosphorus is going to be slower in response than the biological indicators. And then the water column indicators are changing really rapidly. So it's the signal to response issue.
Back in 2014, when Trish brought us a handful of mat, it came from Lake Bel Air. But in Torch Lake, what we were seeing was a flocculent material that settled in the bottom of the ripples in the sand.
Yeah.
Over the time that we've been looking at it, it has developed into mats. Your question has been, well, what changed? Well, I'm asking what changed since 2014 to produce mats.
So it takes time for the species to accumulate and times for the mats to develop. Are you sure that there weren't mats offshore? So the near shore is disturbed by waves. So most of the sampling that you do when you walk in until about here is wave disturbed on a regular basis. And until you get the calcareous algomats developing. So I remember walking into, you were probably, I think, with us when we walked into Ed Gorley's in waders and leaving footprints behind you in the mats. So they were near shore then. And I think once you get this stuff kind of spreading like a disease, it can form more rapidly. You get more rapid colonization from the deep water into the shallow water. And maybe that's what's happening. But yeah.
It's a mystery. Dale's trying to get set up there.
Yes. You've got power, so you're good.
You just try his government computer again. Have any more questions for Jan? I'm sorry?
We're gonna go between Jan's and yours.
Okay, but right now Wayne's up, right?
Yep, so we're gonna use your time.
Wayne, are you ready? Okay, so we're gonna switch. The next item on the agenda is a summary of the mussel survey that TLPA did last year. Dr. Wayne Lancaster from TLPA is gonna give us that presentation. I need
Before I begin, I'd just like to.
Okay, we want to give Wayne his attention, please.
I would just like to mention that this work was funded by a donor who had concerns of the changes in Torch Lake. This is a survey that was done last year by myself, Bob Milron, Lucy Gregoire, Bob Hawkins, Trish Narwood, Andrew Narwood, Wold, and Peg Comfort. And myself and Bob Hawkins manned one of the pontoon boats, and Bob Milron, Trish, Andrew, and Peg manned, I guess that's not the right word, gendered the other pontoon boat. So the rig, the platform is controlled in space in the water with a GPS trolling motor, so we don't drift at all. In 2004, Bob manufactured a couple of these pyramids with the camera attached, with a housing in it, and then spotlights to illuminate the bottom. And we went out in 2004 just to test it, and it was obvious that the drift was just terrible. You had to have something to stabilize that boat. So that's why the trolling motors are used. So quaggas were found in Lake Michigan in 2000. Zebras were found in Torch in 2005. 2015, quaggas are reported in Torch, and then a study was done in 2022 and 2023 by Three Lakes Association, where they were looking at mussel populations using a Ponar grab, which is a device that harvests 6 square inches of, of sediment. As I said, we tested the camera or the device in 24, and then we did the survey last year. Next slide. Here's this is the one that I used. It doesn't have that extension on top. Next one. Next slide. So there were 6 transects. 3 in the north and then 3 in the south end. And so the transect was from, I don't know where it went. Oh, there it is. I can't bend down. Transect is from the shore to the middle of the lake, not the middle of the lake, but around 200 feet. And then from the other side, 200 feet. So there were 6 transects, 1 from each side. We looked at 5 depths, 3 exposures, so there are 140 or 180 photographs that we analyzed. I lost the. Okay. This is what the bottom of Torch should look like. And it's a marl, which is composed of just clay, some silt and carbonate, and some the organic sediment.
I wonder if that answers Becky Norris's question. That's what it used to look like. Okay, where was that spot? The whole bottom used to look like that.
That was probably around 70 feet.
Yeah, that was an outlier there in that spot.
Right, that was an outlier.
Yeah.
Yeah.
That's what it should look like, but it only looked like it in one spot.
Yeah.
I'm not telling where.
Yeah, okay. Go to the next slide. This is what it looks like now. So this is at 70 feet, and it's just covered with quagga mussels. And we have a close up in the next slide. Here they are, and you can see the siphons are these black areas. And when we counted the photographs, that's what we counted was the siphon. And so we're looking at a 2 square foot footprint, and some of these photographs had 1,500 mussels in them. So it took a long time to count. We put a Mylar sheet over the photograph, enlarged photograph, and use a marker and just touch each one. At the time you're doing that, you're counting it. And there were a lot of mussels in some of those photographs. Go next slide, yeah. This is just kind of graphing what it looked like. So we have the north on the top, south on the bottom, west to the left, east to the right. And it would appear that on the east side of Torch, there are higher concentrations of mussels. But if you do the counts, they're almost identical. The number of mussels on the west side of Torch are almost identical to the number on the east side. And in addition, there doesn't seem to be any difference between the north and the south portions of Torch. So mussels are evenly distributed through the lake, as far as we can tell. I mean, it's a very small percentage of the lake was screened, so we don't know if there are areas that have no mussels or areas where the mussels are really piling up on top of each other. We just don't know. Let's go to the next slide then. So based on the bathymetric data that we had available to us, we estimated that there are about 35 billion mussels in Torch Lake. Using this 2x2 grid and counting that we did, and then Three Lakes Association in 2023 estimated about 30 billion, and they're using a 6x6 inch grab of the sediment. So they seem to be pretty much in agreement. But regardless, there's a lot of mussels in the bottom of Torch Lake. Now, there are some issues I think have to be discussed. One is that at 30 feet or so, the mussels are roughly the same size. But if you go to deeper areas of the lake at 80 feet, let's say, you can see very small mussels, these red arrows. So these are juveniles, and the large one, of course, are adults. So there's recruitment in the lake of mussels. So why they don't accumulate at 30 feet, but they do at 80 feet, we don't seem to know. 80 feet seems to be the sweet spot for mussel numbers. We do find them at 215 feet, very few. And in Lake Huron, there's this progression of mussels going from shallow water to deeper water with recruitment occurring in deeper waters. So I don't know if it's a loss of nutrients or crowding, but they seem to go from shallow to deeper water. That's the progression. How do we know if this recruitment is active? We're planning this summer to anchor the boats, drop this thing into the water, take a photograph, pull it up, get an estimate of the mussels, make sure there's mussels there. And because we're not moving, we can drop a ponar down and take a grab and estimate the size, mussel sizes. So from that, over time, we should be able to get an estimate of the rate of expansion and how long it's going to take for them to cover the bottom of the lake, if indeed they're going to do that. The nutrients in this lake are really low, so I suspect that we're not going to see what is seen in Lake Michigan, where the entire lake is covered with the mussels. What can we do? How can we get rid of these things? Well, the genetic manipulation. So the genome of a quagga mussel is 1.9 gigabases. The human is 3.8 gigabases. We encode roughly 20,000 proteins. Quagga mussels, they estimate around 35,000 proteins. So people are looking at the molecular biology of these mussels. I mean, one thing you could try to do would be to sterilize the males and reduce the population with it. And that's so you have 30 billion mussels, half of those are females, and each one of those is shooting out 2 million gametes a year. It adds up fast. So I think genetic manipulation probably is not going to be a major control mechanism. Selective toxins, you have off-target effects, and the toxin dissipates. There's one available now. It's based on a Pseudomonas bacteria that's freeze-dried and fractured, and that material, when it's taken in by the mussel, it disrupts its digestive system, and apparently does not affect native mussels, but that is expensive. It dissipates, and it probably is not something that can be used in Torch Lake. Viruses. There are viruses that infect these mussels. If you have a lethal virus, and you have massive die-off of mussels, would release a tremendous amount of nutrients into the lake, and you'd have a mess, quite a mess. Mechanical methods being done in Lake Michigan, but there's repopulation. And in one study that was done, where they removed the mussels, they came back in subsequent periods of time, and there was no repopulation, And what they recognized was the round gobies were eating the villagers and immature mussels. So there is predation. The round goby, which there are some in Torch, but not, I don't think, huge populations because they're being eaten by the game fish. So that's kind of like where we're at. I think we're going to be stuck with quagga mussels for a long, long time. But the more we know about it, there may be mechanisms to adapt their.
I'm going to take questions while he tries to get transferred to the other computer.
Okay, so I'm done.
When we talk about quagga mussels, is this a singular species that's here, or are there multiple species? My question is this a singular species? Or do we know?
The assumption is it is. We didn't pull any up. Although Three Lakes has done that in the past, and I think they saw quaggas and a few zebra mussels in their collections. But we had no way of really telling what it was because we don't have the ability to get it clean and to look at it.
That we collected for the biomass measurements that Bob and Trish did, Glenn analyzed them. I believe they are all one species. Okay.
Thank you.
More questions? Anybody want to take any quagga mussels home? We've got plenty. Yeah, actually,
Thank you. Very good.
they believe that they are edible, but they're a lot of trouble because, you know, they're almost about the size of a thumbnail. Okay. So.
Tom, in this very limited system, if we have this biomass of quagga mussels that we expect are accumulated over the last decade, so who got moved out?
Well, he's going to talk about how we measured it and what it means in terms of phosphorus concentration impact. But we do believe, based on the pattern that we learned from Lake Michigan, that the quagga mussels have competed and forced the zebra mussels out. All right. So one of the things that Wayne did not mention is we have not done this on our own. We, like many things that we've done in this program, we try to seek out the best minds that we can. So we had a lot of help over time with Mark Rowe and Dr. Ashley Elgin, who was actually a speaker last year for us. So what we've tried to do is as we learn and we measure, we try to compare what Lake Michigan experiences are. Now, when Wayne was going through those numbers, which we also reviewed with Dr. Elgin, our peak number was 3,500 mussels per square meter. A meter is about 3 foot square. And we thought that was a lot of mussels. It looked like that one photograph. So when we asked Dr. Elgin, well, is that a reasonable number? Have we maxed out? And she looked at us and said, we're measuring 10,000 quagga mussels per cubic meter. So what we learned from that, a couple things, is that it's our assumption that Torch Lake is still early in the progression, and we have, unfortunately, a lot of growth. So one of the goals and objectives of the next coming years that the team will be looking at is, Wayne did mention, we want to try to get a handle qualitatively and quantitatively on what this growth rate of mussels is. And Dale's going to talk about what we do with those numbers. Are you ready?
Yep.
Computer's working.
Well, not mine. I'm still on Jan's. Okay. What I want to do now is sort of take everything that Wayne was just talking about and go a little bit further with it. I want to try to figure out what the effects. First of all, Wayne gave you an estimated population. I like to refine things, as you noticed. And then I want to look at the effects on the water quality of the lake. So here is a summary of what Wayne presented. He had a lot of numbers. What I decided to do was to take his numbers, actually Tom and I were playing with this a little bit, and try to break this lake down into a series of depth ranges and look at the average, estimate the population by depth range, and then just sum up the depth ranges. Okay, pretty straightforward. So what we did then is simply take a depth range. Oh shoot, I think I got an old, okay. What we did is we broke the lake down into a series of layers, calculated the area, and then pulled off that last plot the population. Okay. And so when we do that, what we can do is sum this up, and it's close to what Wayne had. Wayne said about 35 million. If we sum them up a little bit different way, we get about 40 million. Now, one of the things we wanted to do is also, Wayne was talking about the size distribution. Well, one of the things that was done here, and I think that was mostly Bob and Trish and Bob, went out there and took some of these, that Ponar, filtered them down and gave me a distribution of the different sizes of mussels. And we just broke them down to big and small. And then, so of that 40 million, I can break it down into how many are large and how many are small. Because what we want to do is to figure out what is the phosphorus content of these guys. Okay. Now, before I did that, I made one more refinement. If you really looked at the numbers that that Wayne was counting, he had one other layer that they didn't really use much. And I tried to take this low end and extrapolate it out, so it sort of tapered off. So it's just a little bit of refinement, taking off that curve I showed before and spreading it out on both ends. So my final population is, is back to Wayne's number, about 35 million. So I come up with 37 billion kind of things, which is close to Wayne's. And now on top of that, we can break it down into how many are large mussels and how many are small mussels. Okay. Now the next step was to take these mussels and I'm hoping I'm getting the names of who did this thing, but Bob's in the middle of these things. Where do you go? Bob and Trish collected a bunch of these mussels, broke them down into big and small, and then sent them over to GLEC for analysis of phosphorus content. And so what GLEC did, and tell me if I'm wrong, took the mussels and we broke them down into like 3 parts: the whole mussel, the shell, and the tissue. And what we try to do is get a phosphorus content of each one of those. Okay, so I'm not going to go into all the detail, but this is sort of what the lab gave back to us. So now we have, for the different sizes, we have the phosphorus content of the shell, of the mussel, and then the whole thing. So now we can break that down to how much phosphorus is contained in all of these guys. Okay. Now, we do have these. I don't know where Bob went. I saw him a little while ago. Anyhow, we have these. So this is from our study right here. And so this is all the numbers straight out of GLEC. We looked in the literature and we asked Ashley about, do these make sense? And they're all sort of in that ballpark. Yeah, you can always be a little bit more specific and say, okay, we got 0.2 milligrams per kilogram, they have 0.1. It's a big difference in some ways, and it's a very small difference in other ways. But anyhow, it gives us a good estimate of how much phosphorus there is in these guys. So now the idea was, and I don't expect you to follow all this, just get the general idea. We start off with a population, multiply it by the milligrams per kilogram, and ultimately we have the big ones, we have the big ones and the small ones, add them all up, and we get 1.55 pounds. No, we got a really accurate number, precise number, I should say. It isn't accurate. And if we put that all together, what we end up with is, we end up that the amount of mussels out there, when you break them down to big and small, we estimate that, keep hitting the wrong button. We estimate that there's about 1,500 kilograms of phosphorus tied up in these mussels. Okay. Now, if you remember right, I was saying that on an annual basis, about 3,700 kilograms come in. So that's about, getting close to 50%, or a little bit over 50% of a year of phosphorus is tied up in the mussels right now. Okay. So if we look at this, and now we're saying, okay, how much of that, how would that, the amount of phosphorus going into the mussels impact the water quality of the lake? Well, if you make a few assumptions, and first of all, Wayne was sort of getting at some of this, and we talked to other people, and this might be a good ballpark. that a mussel lasts about 4 years. Okay. It turns out that shallow mussels may not last that long. Deep mussels might last a lot longer. But on average, it's about 4 years. So if you take that and say, okay, 1/4 of all the phosphorus tied up in the mussels is getting put in there. We're sort of looking at a snapshot in time. So right now, 1/4 of the phosphorus in the mussels is coming in a particular year. Out of what's coming into the lake is going into the mussels. On top of that, 1/4 of the mussels are dying. And so we want to look at 1/4 of the phosphorus tied up in their shells. So if you add that up together, it looks like on an annual basis, we're losing about 432 kilograms of phosphorus. Okay. So what does 432 kilograms mean? Well, one possibility, I like to go back to my Canfield-Bachmann model and say, okay, let's go back into here and drop it 432 kilograms. Just bump it down, and that's a percent, but you can do it. And based on that, you go through this, you get a little bit of a drop, and it turns out that my first guesstimate is that the effects of zebra mussels last year would have been to drop the phosphorus concentration down by 0.4 micrograms per liter or 0.0004 milligrams per liter. So is that big? Is it small? Well, we only started off with 4 milligrams per liter, so that's a 10% drop in phosphorus concentration. So is it having an impact? I think it is. Okay, so this is one approach to estimating this. Now another approach is there's papers out in the literature. And Sergey, I've been talking to him, and he's a 4th author on this thing, but a lot of it's based on this paper that he wrote a few years ago. And what he does is goes through, and first of all, he needs sort of that change in the population of mussels. And based on this, we came up with, here's our description of how I think the mussels have changed through the lake. It's just a guesstimate, but it gives us around, you put those numbers together with what Wayne had on and Tom have. 1980, we didn't have any. 1990, a little bit, and we have a few measurements that are sort of in there. The 1980 is sort of a measurement. I think the 1990 is when zebra mussels came in, and then we come up and they're all quaggas. And I said, okay, what happens if we were 30 some billion today? What would happen if they go up to 60 billion and then levels off? So that was my guesstimate on what it would be. And I said, can you put this into your model and tell me what your model is going to say that its impact would be? So he goes in there, and here's right now, I just said for the first guesstimate, I've got 3 guesstimates. Let's just assume that the phosphorus load hasn't changed. We kept the mussels, they came in, but the phosphorus load is today's loading. Okay. What would be the effects of the mussels? Well, here's the mussels in his model taking up phosphorus. He hasn't broken down in there. I gave him the mussel characteristics that we had, and so those sort of are incorporated into it. And when you look at that, don't worry about this little increase. That's just the model coming to equilibrium. But then it goes through here, and then the phosphorus, as the population goes up, the phosphorus concentration in the lake starts to drop. And that's the zebra mussel, or the quaggas mostly taking up that phosphorus out of it. And based on that model, comes up that the mussels should have an effect of about 0.000. There's a lot of zeros there because I'm looking at milligrams per liter, but that's 0.28 milligrams per liter, or micrograms per liter. So one approach was saying that it was 0.0004, one is the other is 0.003. So either way, it looks like the mussels are having an impact. It may not be a huge, but this is still 10% of basically almost 10% of the phosphorus coming in is being taken up by the mussels and dropping the phosphorus content in the lake. Yeah, both of them do. Yeah, yeah. So, yeah, now if you looked at my approach, that was, there was the 2 pieces of it. But when they die, every year they die. So once they get to that equilibrium stage, what comes in goes out. So unless the population is changing, that part disappears. So if I looked at those 2 pieces, if the zebra mussels or the mussels in general leveled off, all you have is a loss to the shells. The rest of the part that goes into the tissue would be taken up by the new tissues. So, okay, so as long as the population is increasing, it's basically taking it up, except for what you lose in the shells.
That's one of the reasons why it's so important to find that point where it does in fact
Right. Yeah.
level.
But right now, there's the two approaches. Mine is pretty simple. The other one is pretty complicated. It's based on sort of, it's not the most rigorous model, but it's one that, it's a combination of models. Sergey came up with a fairly simple lake model, and then onto that, he put all the muscle dynamics into it. So it's taking up how much phosphorus is going into the muscles, how much is coming out of the muscles, and that's why when you look at his approach, he breaks it down to how much is in the muscle, how much is live muscles, dead muscles. I honestly don't know what each just is, and then the shells. So, yeah.
So does this assume that all the phosphorus excreted in superficies and then the phosphorus in the tissue itself stays in the water? Or does it consider that when they die, a lot of this sort of particulate matter just kind of rolls downhill? So permanently lost.
There is some permanently lost, but I don't think there's any permanently lost in Sergey's model. I don't think there's any permanently lost that way. There is lost out the outlet because he has an outlet. He has that part, but I think that part is regenerated back into the water column. So yes, it goes into pseudo. Right. But I think my own gut feeling is that when I looked at those big numbers, going from 5,000 to 20,000, that's a lot of this stuff going on. So I think what happens is that when we're generating, I think this going from 5 to 20, it's a combination of your GBA dying and that kind of thing, and these guys. So I think it's a combination. How can I go from 5, whatever, I can't remember the units on it. I think it's 5,000 kilograms up to 20,000 kilograms. It goes up like this, and I only get 3,000 that I'm putting in, so I got this huge 15. This is all biology. I think it's a combination of the GBA and the muscles that's making these changes. So when I'm getting stuff being taken up, I think that's the algae in the bottom growing, not just out in the water column, but if it's algae in the bottom growing, it's going to be taking it out of the water column, and vice versa.
What are the muscles? What phosphorus they use for shells and eventually it goes
Well, in general, what they're doing is they're filtering the water column, so they're taking it out of the water column,
Putting it in different form.
putting it in different form.
But they also have to survive on something. That's not their main job. Their main job is to
Right.
eat. So
Right,
what
well,
are they eating?
That's what Jan was sort of saying.
So they're eating nitrogen. They're eating something.
Well, they're eating phosphorus and nitrogen.
Right. The phosphorus isn't destroyed.
Neither is the nitrogen. They're just eating it. They're
Yeah.
just eating algae. If you look at them, what they're doing is they're filtering all this stuff out, and yeah, they kick out a little bit of dissolved phosphorus as it goes through, but then a lot of it goes
Well,
into
the filtering capacity is pretty large for, I mean, when,
Well, it's
when you're
tremendous.
saying 36 billion times
Yeah.
whatever.
Oh, we could go
a
through
liter
it.
a day.
We could go through and tell you how often it flips through the whole system.
So there's got to be more of a chemistry impact, I guess, is what I'm getting at.
Yeah.
Do the calculation.
20 days. Yeah.
A full day per muscle.
Yeah.
A liter per day per muscle based on the volume of the lake, which is 0.78 cubic miles and blah, 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 ends up to be about 200 days. It can filter the entire lake. I think it's
I don't know
200
exactly
days,
what
I
that
think.
is.
Yeah.
But when you're looking at this, I think this is the reason why when you're looking at the mass of phosphorus in the water column, why it's changing at different time periods. I have to go back there and look at it and see, am I losing phosphorus from the water column at the time when these guys are starting to grow? I don't think it's the right timing for that, because I think we're losing it to something. It's disappearing from the water column was mostly in the fall, and I don't think any of these things. So I think the biology has a big handle on what's going on here. It's going to be a reaction at that interface, a combination of the muscles, the GBA, and other things that's causing this sort of internal loading and internal take-up. But I think the bottom line is that the muscles are having an impact on things, and I think that as we go into this next discussion, I think the muscles are also having an effect on factors that are driving GBA.
Okay. Then there's your cue. I guess we get to go to the next discussion. And then after this one, we're going to take a little break. And was I promised cookies for the next break? Okay. The next break, we get cookies.
Tom, I decided to go in a different order.
I'm sorry?
I'm going in a different order.
Okay, it's fine.
It's the same idea. Okay. Now, one of the things I want to do is go a step further on that and try to find out, can we get a little bit better idea of what possibly is driving the GBA in the lake? Okay. So what is the variability and possible causes of GBA? So when we look at GBA, we really have three different ways to describe it. Okay, at least that's the way GBA has been described in the past, three different ways. One is the way that Jan was talking about it. So when we started this study, I asked Jan, could you tell me, we got these sites around the lake, can you give me 12 sites that have low, medium, and high GBA? Okay. So these numbers are based on Jan's original numbers. A blue is low, a red is high, and orange is in between. So those were his, for these 12 sites, that was Jan's original numbers. Tell me if I lie. Then he went through and, as things evolve, he said, oh, we're changing it a little bit. And he said, well, that site up here, if you look at it, like one was red and it turned to a different color. So we have a little bit different way of describing it. Then we sent out our own crew. And Jan, I don't know if you heard about this or not, but we had Dan, Tom, and Jim, who just took off, said, go out there and you tell us what, not GBA is, but this is where we get into it. Just tell us the benthic algae. Go out there and say, for all of our 12 sites, give us a score of 1 to 10 or 1 to whatever it was, 1 to 5. And so what we do is we have three different ways to describe these 12 sites. And again, now what we want to do is to say, this gets in with some of the stuff that Wayne was, remember I said we were going to go to all of our sites and we're going to collect the magnesium, the iron, that kind of thing. So what we wanted to do then was to try to go out there and what can we look at the data that we have at these sites, can that help us a little bit? So we have a whole mess of information at each of these 12 sites. We've got the temperature, the conductivity, the pH, And then in August, we also have iron, manganese, magnesium, molybdenum. And what we wanted to do then was just simply throw it into a regression and try to find out. And now, before I did that, I standardized it and did a little statistical manipulation of the data just so that everything's on the same playing field. And the bottom line was, if we look at Jan's original numbers and said, okay, based on that scale of 1 to 5 or whatever, I think that's what I put on it, can you tell me what is the most important factors driving it? And it turns out that if we look at the first one, which is Jan's original numbers, came out that dissolved iron, total nitrogen, conductivity were related. Jan, I'm hoping this gets you ideas. All this is trying to drive ideas on what could be factors driving this. So that was the first one. We did the same thing with the updated numbers. We're only dealing with 12, so it can have a quick change around. And if we did it again with the new numbers, temperature, chlorides, and phosphorus were the most strongly correlated. I'm not going to put any p-values with this because I'm sure they're not going to be there. And finally, when we looked at the TLPA index, nutrients like dissolved phosphorus and ammonia and iron, especially in anoxic areas, were the most important factors. So what we're trying to do is just get an idea of what might be driving it. And it sure looks like in most of these kind of things, we're getting this idea that, now this is the phosphorus coming out of the groundwater. This isn't phosphorus in the water column. But it looks like even though phosphorus is going one way in terms of getting the GBA to grow, if you looked at the concentration coming out of the water, it's having the opposite effect. So one is getting the species that you want. And that's Jan's whole picture. The other one is saying, once you have them there, what drives the variability? So low phosphorus may be causing the right species in the water column, but the phosphorus coming out of the bottom may be causing, driving them a little bit more. So once you have the phosphorus, could it help the variability? Well, dissolved iron, this is what I'm saying. I'm not going to put a p-value with this, but this is the kind of distributions that we're looking at. So if we had dissolved iron versus Jan's original score, or dissolved phosphorus versus the TLPA score, we're trying to see if we can get these factors. Now, with only 12, it's hard to get this, but this might potentially drive a little bit of a future study. This is groundwater, because if I did that for surface water, it'd be a constant. All of them would have the same value. But we do have, when we looked at this, we did have the groundwater and we had those concentrations right next to it. These are all groundwater concentrations. So, just a theory, or not a theory, but that's just what we're coming up with right now. And the last thing we wanted to talk about is trying to put this all together and Tom, I really don't even know what slides are going to pop up here, so we'll try it. So what we're trying to do ultimately is take everything that Jan did and add a little bit to it. And for the most part, what we're looking at is trying to say why. If you remember from the very first, when I first started talking, I said something happened around 1998 to 2004. And it sure looked like something around there caused a big change. So this is sort of a summary of some of the stuff that Jan has presented in the past. We got this calcium carbonate layer. We have 3 layers in his GBA. And what we're ultimately trying to do is mostly look up in this top layer and trying to describe what's going on. So when we look at this, what really changed as we're going through time? You know, if we go back to 1995, when we first came here 3 or 4 years ago, we were talking about this publication, National Geographic, about this gray matter around the lake. And the gray matter just seems to coincide with, now that we look at all this, it seems to coincide with when the pH of the atmospheric deposition changed, which that's one of the things, and it just happens to coincide with that. But if we look at some of those other things, it's not just the pH range. You look at the introduction of mussels. That happened around there. Possible decreases in phosphorus. It's hard to say, but you know, we don't have data that goes back that far. But there's at least a hint of an indication that that phosphorus concentration dropped. If you remember that first slide, I was showing the high numbers. We didn't have a lot, but it looked like it dropped. Everything that we have with calcium carbonate increasing should have dropped phosphorus concentrations. There's all these reasons why phosphorus should have dropped, which would cause everything that Jan was talking about, sort of a change in the species kind of thing. So that could be part of it. Now, I told you it was sort of weak, but we have groundwater coming in. And the groundwater, if the groundwater is underneath these algal mats, it almost acts like like an agar plate with these nutrients able to dissolve out to them to keep these things growing. So we really think that it's a combination of all these things that's causing. So GBA is not a one kind of thing that changes everything. Could it be just the phosphorus that changed that species shift? Maybe, but it did coincide with the mussels and with that, with the pH. So we talked about those factors. Here's when we're looking at this first thing that I think may have been the real reason why this whole thing even started in the first place, was this change in the amount of acid rain coming down. If you look at the timing, it's pretty close where the amount of phosphorus in atmospheric deposition started to, the pH started going up. But at the same time is when we've seen that pH in the lake change. So that's one of the factors driving it. That would have caused a little bit more calcium carbonate precipitation, which could cause the phosphorus to drop down to below some of Jan's critical numbers. All of a sudden, that could start to change the species distribution in the lake. Clarity, I don't know. You know, there's that little change around 2005. Could this make a difference? Possibly. In the literature, it says it's a little bit bigger difference, but in this lake, it's clear. And now, even in the middle of the summer, you got at the lowest, a 5-6 meter Secchi depth. I don't know if that would make a difference, but it could. And we do see that. And that happened to occur with this. Is this just a side effect of the changes in calcium carbonate and the mussels? Mussels are going to make it clear. More calcium carbonate precipitation should make it more turbid. So if we didn't have the more calcium carbonate precipitating, we might have seen a bigger jump. So if we look at this whole time series going through here, a lot of that stuff, it's sort of in that in this 2000 range, where all of a sudden we got everything changing. We got the precipitation, we got the acid rain and the mussels both coming in the same time. It sure would have been nice if they would at least separated in time a little bit to help us try to pull these two apart. But right now, it looks like one sort of led to the other, or let the one thing happen. So like the mussels may have came in, and they could also bring that phosphorus concentration down a little bit. I showed us a 0.5 milligram per liter in some things, but it could also change that distribution of where the phosphorus is. So overall, it looks like there's a series of things coming in. And if you started this, okay, we got the water quality, nutrients, and sort of the other species. Well, let's forget about the other species. We got the water clarity, nutrient changes, and the pH changes. Now that, at least our theory is that led to Jan and Jan's whole thing. So we got these changes that are coming in. Then it's a whole biological thing. It's a change in one type of biology to another type of biology. And it's that shift from systemic to the other one. It's hard to say. So I think the bottom line is that, and this just goes a little bit further, we see that little bit difference in phosphorus concentrations in that could be feeding it. So I was talking about today, and there's a little bit of a correlation. We have higher GBA in some of these areas with higher phosphorus concentrations coming in from the groundwater. So that's basically a summary of all that. So we got a lot of things changing, and I think if we look at this as the big picture, I think it's a combination of, the only thing we're really doing is taking Jan's whole talk and saying, okay, Jan, this is what we think may have led to the perfect storm for Torch Lake and probably a lot of lakes in the area, because now this pH effect, that's going to be this whole area. The mussel effect, if they have mussels, most of them are coming in about that same time period. So it could be shifting a little bit one way or the other to have the effect. So, and then ultimately, we think groundwater, although you would think groundwater is going to raise the phosphorus, if it's trapped in the right place, it may not allow that species switch to occur because it's not getting out to the suspended algae. It stays in there for the benthic algae. So with that, I think I'll leave it wide open. And what do you think?
I think there are a lot of errors. I do, because we tested a lot of those hypotheses early on. And if you know algal environment responses, for example, we put open and closed, we made PVC circles, put them on the bottom of the lake, put a plastic bottom across some to prevent groundwater from coming in, and then not the others. Came back the next year, sampled, and there was as much algae, so kind of let it go over winter and have a chance to develop. There was as much algae, they look exactly the same.
The only thing that comes in with a few of those is that I'd like you to redo it, but do it in front of Peg's house. No, do it in a place where we know that there's a lot of groundwater coming in. Because one of the things we found is that there's a lot of places, you saw our heads, there's a lot of places that groundwater just is not doing much. And it would be interesting to look at this and do it in a place where we think there's a big phosphorus gradient or something, and see if that could do a little bit.
So when we manipulate,
we have the exact data by site.
I understand that.
Yeah, okay.
There's just too much here to argue in the next, I could, if I had notes, maybe I could keep up with all the things that are out there, but.
Well, how about if we did it? We'll just
Did what?
duplicate. We'll pick the sites that we know have the groundwater influence, and we'll duplicate your experiment with the Mylar bottom.
Go for it.
Okay.
Yep. So the other thing is, you're talking about these species not, and the calcium carbonate deposition not happening in more alkaline waters. And I explained to you that in an email that the waters of the Everglades where these calcium carbonate mats develop are circumneutral. So pH is not going to have an effect on the deposition or an ultimate, a strong effect. You get really thick mats in the Everglades, same species, many of the same species, not exactly the same species. I don't think water clarity is important with the zebra
I don't either.
mussels. I just think it's a decrease in phosphorus in the lakes, which
Right.
is really well documented throughout the region.
Right. But that's where, if you follow this, I agree with the clarity. That's why I said when you look at it, it's just not much of a change. But when you look at it, I think it's a combination of the mussels and the pH that brought your pH down to drive this. So I think this is what,
No, the pH went up, didn't it?
oh, the pH went up, sorry. The pH went up. When the pH went up, then the phosphorus came down because of more calcium carbonate precipitation. So I think what happened was there's two different things. The mussels would have removed it from, the mussels were filtering a lot of that stuff out there and moving the phosphorus from them.
I don't doubt that the mussels had an effect
Yep.
on decreasing phosphorus in the lakes.
Yep.
I think there are a number of different mechanisms that cause a decrease in phosphorus in the lakes.
Right, and that's what I try to show is a few of those.
Yeah, a few of them.
Yep.
And then, so it's basically a decrease in phosphorus in the lakes. And I think that the ground, so if you give calcareous algal mats more phosphorus, based on experiments that we did in the Everglades a number of different ways. In fact, one of my students took mats from the glades, came back, put them in a pond with low and high phosphorus in them. And the mats lost calcium carbonate within 3 days of being exposed to phosphorus.
Right, and I think that's where,
So phosphorus from the groundwater, I do not think is going to stimulate the development of the GBA. It might be nitrogen from the groundwater that's correlated to the phosphorus that's making the GBA a nicer golden brown.
yeah, that's
But-
what we do actually, when I was showing that first part of it, when we looked at it, we didn't look at GBA. In fact, it was, like, we got rid of the G. It's just benthic algae.
Yeah.
So this may be a combination of two things. One is that when we looked at that index that said that phosphorus was important, that wasn't your GBA index, it was a BA index. And that's where all of a sudden, when we look at this, we want that's why I was asking about the benthic algae and whether we can do it from satellites. We might just be getting benthic algae and we're not getting GBA.
Right.
And that's where it's going to be hard unless we know what we're using. And so if I had really good numbers on that, so we had 12 of those. Those are your numbers. Those didn't correlate with phosphorus.
They don't.
But no,
Yeah,
and they didn't on mine either.
Yeah.
Only when we looked at the benthic algae, when somebody looked over and said, this looks bad,
Right.
this looks good. That's the one that it worked with. And so we're going to always have problems unless we have somebody to say, that's a GBA, that's a BA.
Like somebody going in 20 lakes to find out.
Right. No, that's why when we look at this, I think there's going to be a reason why benthic algae's gotten worse.
So I don't know. So one reason is, why do we need to know what caused the low phosphorus and the GBA to occur? Is there anything you can do about it? I mean, intellectually, it's very interesting, but I think it's a lot of hypotheses that we can't test.
I completely agree with you.
We
It's
can
just sort of a-
speculate about them on first principles, but they have to be consistent with the biology.
Right.
Right.
And that's where, if you go back, the big change happened in the year 2000, give or, right around there.
Changing what?
GBA
wasn't here in 2000, from what I know.
Right, but there was the gray matter. So if you go back, so when we first started this thing, if you go back and you look at all the literature and when they put this together, the very first thing that got this group together was not GBA. Well, not even this group, the group before this group, Yeah. If you look at it, that first thing that came out was not an interest in GBA. It was they were concerned that this benthic gray matter was the concern. And then after that was a concern, then GBA came in after that. And all this is trying to do is to say, if we look at the long-term history and the problems of water quality in the lake, the first one was the gray matter. Then it was sort of the GBA. And maybe the next one might be just the BA.
Well, or they're not related.
They might not be, but they should.
Right.
But
So-
right now, if you look at the change in the, that got, the original group seemed to appear about the year 2000.
What happened in 2000? I'm kind of losing.
Well, the 2000 is the pH, which would have been the benthic algae, not the benthic algae. That would have been the gray matter.
Yeah.
So it was the,
Yeah.
we think that's what started this whole worry about water
Right.
quality of the lake.
Yeah.
And it was,
But I'm not sure how you're connecting that to GBA.
well, GBA is, if you look at those
You're-
layers.
You're suggesting multiple mechanisms and it's confounding the
Yeah.
the model
Well-
in my head.
Well, would you,
Yeah, it's that the bottom layer of what you have is,
No, okay. The gray matter that deposits on the lake is an inhibition to the development of benthic algae. The algae develop on top of that, and then they precipitate their own gray matter. The best mats are on sand. The best mats develop on sand. The mats that I, have grown in these different experiments are on sand.
I thought that in order for the mat to develop, it had to have a base of calcium carbonate precipitation and then developed over that.
They
So-
precipitate the calcium carbonate. So that's why on an Everglades Eleocris stem, a macrophyte stem, these calcareous algal mats develop like, they're called sweaters around the Eleocris stem. And then they become so buoyant because of the oxygen produced, and then they float up to the surface. These mats, the place, so for example, Becky's Beach up in the northwest corner had
sand.
tons of calcium carbonate.
It's all
Um,
sand.
And it's all sand now?
Isn't it all sand? Becky's Beach? Yeah.
When I was up sampling at deeper at 5 or 6 feet of water, I noticed a lot of calcium carbonate laying
Oh,
there.
okay, but the base is not rocks like a lot of Torch Lake is.
No, but it was calcium carbonate over
Right,
the calcium precipitate. It was the slowest place to colonize. It was other areas that colonized faster.
You have to be able to eat calcium carbonate to qualify.
Yeah.
All right. Up at Becky's Beach, it's a sandy bottom, but about 6 to 8 inches below the sand, it's all marl.
Thank you, Ben. All right, we're gonna continue this discussion over a cookie. All right?
Tom, you're a meeting coordinator. Keep it moving.
that was one of my big concerns was that benthic failure, whether it was the thing or not. But especially in your picture, when you drew it up, I'm going, shit, that's not, because you had the little particles inside of it.
Yeah.
That's what he was saying. So yours follows his thing. It just killed my theory. Because what happens is the GBA is forming that, and that goes with wanes, as he was saying, got slimy first. And so it's.
I never heard, but I guess. Can we get close to coming back in about 2 minutes, please, so we can start to wrap this event up? I'd like to remind everyone that before you leave, if you could please take a little bit of time and share with us, either by way of a 3x5 card or a piece of paper or email, something, what you can do for us, which is very important to us, is leave us a statement of what you feel you got out of this session. We covered a tremendous amount of material today, a variety of subjects, all related to Torch Lake, but we are not completed with this journey. And what your thoughts are on what you've learned, what you believe was important from this session, is going to help guide us in the coming years. So we would very much appreciate if you could just take a few minutes and write down those things, because like I said, we started this journey 6 years ago. We're not going to end it this year. Torch Lake is too important to all of us. Okay, so 323. We're really not that bad off. Well, you have some kind of a protocol in there that decided. Hey, if we can all get back to our seats, we just have one more brief presentation. And we're going to try to cover any more questions, but the last presentation is really, now that we've gone through this review today, and we get your input, hopefully, and I'll send you an email reminder for your input, I guess. Where do we go from here? When we started this, we were in search of what is the state of Torch Lake? How did it get there? Where's it going? It took us on a lot of sub-paths, but our original goal and our original plan and our original vision still stays the same, because what we owe to the generations that follow us is the same beautiful, majestic lake that we have been able to enjoy. So with that in mind, what is going to happen for the rest of this year, 2026, and what happens beyond that? The picture that you see, which is taken from a shoreline in Torch Lake, from my wonderful neighbor's airplane, he took me up. Sometimes in order to achieve clarity, you have to take a 5,000-foot level of things. And that's where the majestic beauty of Torch Lake can really be appreciated. And yet, for all its beauty and immense size, Torch Lake is a very fragile ecosystem. You heard a lot of things today. One of the things that I hope that you write back to me that I've heard is we're looking at very small numbers where percentages of those small numbers or small changes can represent a big problem for Torch Lake. It's wonderful to be a beautiful lake with low nutrient numbers, but it's also dangerous because there are many things that can affect us negatively. So one of the things that we believe is that, like a young child, Torch Lake requires protection and care. But it's it's up to us, I'm sorry, in order to implement processes and education to maintain that. We are a very small number and percentage of people when you compare us with the businesses and riparians that are involved in the chain of lakes. We cannot stand by and let those people damage our resources through neglect or simply lack of knowledge. So we have to educate and we have to regulate. We have to do that by influencing the people in a township such as this township, in the county. The way we're going to do that is with a science-based factual report. And that's what is so important about what USGS has been doing for us and is going to do for us this year. The other thing to remind is, although our focus has been Torch Lake, we are part of a beautiful chain of lakes, and we're all connected. So we have to make sure that our stewardship extends beyond Torch Lake itself. So what are the milestones for this year? The first milestone is this report. So USGS is going to prepare a final report. You saw the core context of that report today. The content of that report is really the science. It's collecting the data, analyzing the data, drawing key findings from that data. And they will work on that analysis. They'll finalize the report. It'll go through an internal peer review process at USGS, where multidisciplinary people will take and go through that report. That report will eventually be published, we're hoping by the end of the year, maybe early next year. But it's going to be something that will be publicly available online. They don't print them hard copy anymore, right? When that becomes available, I'll use all my distribution lists to let everybody know this is how you go find that report. This is important that we make use of this information to protect the chain of lakes. The second milestone is a parallel effort as USGS takes this to the formal report stage. Although I think Dale's getting tired of me sending him emails 2 and 3 times a day. We, TLPA and TCC, we're going to work in parallel with USGS because we have to translate the science into recommended actions, management actions, and recommendations. Things that we can communicate to the townships, to the county, to the riparian landowners. What can everyone do to help preserve and protect this wonderful resource? And that's going to be our goal and our job. So we're going to work in lockstep and in parallel with USGS so that we do that correctly. The third milestone, we can't stop now. A lot of the things that you heard about today is the fact that we struggle science-wise for drawing clearer decisions or conclusions from the data. And the reason why, repeatedly, is we have difficulty defining the history. In order to protect or change that going forward, we have to make sure that we develop a long-term monitoring program that's well documented, well understood, and well formulated to watch the right things so that the people that follow on beyond us from a future standpoint will have that record. Last year when the gentleman, Steve Hamilton, came in from Lake Leelanau, he came up and he put his chart up there. He had 20 years of data, consistent data. The same labs using it, the same protocols, very valuable data. We did not have that opportunity. We want to provide that opportunity to those that follow us to make sure that they have a sign when something starts to change, they'll be better prepared to do that. The fourth and ongoing milestone is to take the work that we've done and make sure that we can expand its use and understanding within the overall Elk River Chain of Lakes Water Improvement Plan team. So we are part of that Urkel Whippet team. We are, have been sharing updates. We will continue to share updates. And then in earnest, when the final report and our recommendations come out, we hope that we can make that not effective just for Torch Lake, but to expand that beyond into the entire chain of lakes. So that's the key milestones for this year. What's our formula for success? It's nice to say that that's what we're going to do, but how are we going to do it? Well, we've had we've learned by getting kicked in the teeth a couple times, but we've learned a couple things. The first one is we have to develop a organizational structure within TLPA so that an ongoing effort to establish this lake management group, the people you met on our project team would be basically a new lake management group. But we have to make sure that we have the skill sets and the tools. Like Bob brought in that little camera fixture. It had to be invented, it had to be manufactured. All this was done on, basis of volunteers. It's much easier to have an organization with more than just a couple of volunteers. So we have to focus on that, like from a management perspective. The role of a management is give your people the resources, the time, and the budget to go get their job done. So we were to start with that. We're going to have a clear goal for that managed group, working group. And that goal is going to be to establish a credible, ongoing lake monitoring response and reporting system that uses science to drive priorities, policy, and public trust. Very clear goals. Now, the next one's a little bit tough. It's not in my DNA, but we have to do it. These things are expensive. This project that we just wrapping up with the USGS was a lot of money. We were able to secure the funds, but if we're going to be successful ongoing, we're going to have a successful fundraising effort. And that effort's got to be tied in with what those goals are, because it's sort of like an insurance policy. if you don't have the money and you don't do the job, when a problem shows up, you say, well, you should have had insurance. You should have been doing the monitoring. So it's up to us to convince the people that have the means that it's worthwhile to invest a little bit of money in this lake and in this resource. And again, hopefully it goes beyond Torch Lake. The other thing is that we need people like Jan and we need people like Dale that have the technical knowledge and expertise to keep us on track. And that we would call an advisory board. Certainly, I'm a mechanical engineer. I've learned more in the last 4 years than I thought I ever learned or wanted to learn. But it is important for me to be able to help put back and give back to the community what I've been able to achieve by living on Torch Lake. And that's why I do it. And the last is the long-term sustainability goals. If you look around at those of us that have been working on this project, we don't have that many years left. So we have to encourage and develop young people to have the passion for this beautiful resource that we've been able to enjoy, so that as we pass the baton, they have some experience and some knowledge, some good data to work from. So sustainability is going to be very important from a human standpoint. So with that, I'll take any questions. I would also like to remind everybody that whether you responded or not, everyone is welcome to join us for a social hour at Torch Lake Cafe, just up the road a little bit, north of here, immediately following the meeting. And then we're going to go from the social hour into a dinner. But any questions? You don't have to be that quiet. All right, well, then I'll thank everybody for their time, and I hope that it was valuable to everybody. I will send you an email. Keep thinking about us, because I really want to know what you learned today, what your key takeaways were from today.